Hello everyone, welcome back to General Chemistry. In this video we're going to go over a lot of stuff to do with ions. We're going to go over acids and bases and oxidation and reduction, and then we're going to talk about titrations and we'll wrap it up with that. And of course, just like last time, we'll have a lot of example problems to look at. So without further ado, let's begin. Okay. All that's set up. So, last time we had a problem that involved an acid-base reaction, and I said that it would be better to postpone it until we talk about acids and bases. So let's go ahead and define what acids and bases are. There are actually different definitions for acids and bases, which we will cover in a later chapter when we learn some more advanced concepts. But for now, here's how we are going to define acids and bases. An acid is any substance that gives us additional hydrogen ions when it dissolves. Any substance that increases the number of hydrogen ions, H plus to be specific, when dissolved in water. A base, on the other hand, will be defined as anything that increases the concentration of hydroxide. So rather than rewriting all of this, I'm just going to say increases hydroxide concentration when dissolved in water. Okay. So let's take a look at a couple of examples of that. So we already know some acids from part 1 when we actually practiced naming acids. Let's take, for example, the go-to acid that always comes to mind whenever I think of acids. The first one that comes to my mind is hydrochloric acid, HCl. So hydrochloric acid, when it's in aqueous form, it separates into hydrogen ions and chloride ions. All chlorides are soluble except for silver, mercury 1, and lead 2 chlorides. Hydrogen is not one of those exceptions. So this thing can dissociate into a pair of ions like so. So basically, when you have it in aqueous form, you have some hydrogen ions floating around in the water. Another example, so for a base, let's say we've got sodium hydroxide. That's the classic base that I think of whenever I think base. Whenever you dissolve this in water, all alkali metals are soluble with anything and everything. Since sodium ion is in here, we know that this can dissociate into sodium ion and hydroxide ion. So this is a base because it produces hydroxide ions when dissolved in water. Now, there is another example of a base that's a little more obscure, and that is ammonia. Ammonia, NH3. When dissolved in water, it increases the hydroxide concentration, not because it dissociates into hydroxide, clearly it doesn't have any hydroxide in it, but because it reacts with the water itself. So what it'll do is it'll take a hydrogen off of the water and form the ammonium ion NH4+, but it'll also leave behind hydroxide. Once water loses a hydrogen ion, what's left behind is a hydroxide. So ammonia is also a base under this definition. Okay, so those are a couple of classic examples of acids and bases. So where do acids and bases come from? How are they formed? At least the acids and bases under this definition. Generally speaking, acids are formed whenever you add a metal hydroxide, or sorry, a non-metal hydroxide, I should say, not a hydroxide, a non-metal oxide. I'm off my game today. A non-metal oxide reacts with water. And bases are formed when metal oxides react with water, specifically in combination reactions. So let's take a look at some examples of that. You might remember back when we covered the solubility guidelines. In fact, I should probably pull it up. Yeah, let me put that up on the screen for you. If you look under rule number 5, it does mention that all metal hydroxides and all metal oxides are insoluble, except, of course, those of group 1A, which is the alkali metals, the red block of the periodic table that we use, and calcium, strontium, and barium. But there's also a note where it says when metal oxides do dissolve, they react with water to form hydroxides, and they have that example reaction for you. Sodium oxide plus water gives you sodium hydroxide. Let's take a look at another example. Let's say we have I guess we'll start with bases. Let's say we've got calcium oxide. Calcium oxide, when reacted with water, will give us calcium hydroxide, CaOH2. Calcium oxide plus water gives us calcium hydroxide, which is a base. Okay, and as for an example of an acid, let's take a nonmetal oxide such as dinitrogen pentoxide. Dinitrogen pentoxide. If this reacts with water, then what we get is nitric acid, HNO3. And if I balance this, let's see, I would need a 2 here. Second equation down there is already balanced, so nothing needed there. But let's see, 2 hydrogens, 6 oxygens here, 5 plus 1, 2 times 3, that's 6, and 2 times 1 nitrogen there gives us the 2 nitrogens there. Okay, perfect. So those are examples of how acids and bases can be formed, but of course, like I alluded to earlier, there is a later chapter that we will see once we learn some more advanced concepts where the definitions of acids and bases change a bit to include more substances, and those additional substances are not always made through this process. The reverse of this can also happen. So if you heat an acid or a base, typically heat is enough to decompose the acid or base into whatever 2 substances you have to put together to make them. So if I heated calcium hydroxide, for example, I could get it to dissociate into calcium oxide and water. If you have the type of teacher that likes for you to predict the products of a reaction, then this is one of those patterns of chemical reactivity that you may want to know about. But in my experience, most teachers don't really care about teaching that, which is a bit of a shame, but it is what it is. Now then, where do I want to go from here? So we defined acids and bases, and we've shown how they're made. Now let's talk about some acid-base reactions. So some substances, as we know, don't really dissolve well in water. One example of that is calcium carbonate, CaCO3. This doesn't really dissolve well in water. It follows one of the solubility rules, saying that carbonates are generally insoluble with the exception of ammonium carbonate and the group 1 metal carbonates. But yeah, calcium carbonate, chalk. It doesn't dissolve in water. Chalk, limestone, I guess one of the major components of cement, does not dissolve very well in water. However, we say that it does dissolve really well in acid, and I don't think the word dissolve is appropriate here, but that is something that people say. If you react calcium carbonate with some sort of acid, let's say we react it with hydrochloric acid, for example, then what can happen is the hydrogen replaces the calcium while the calcium replaces the hydrogen, so it's another one of those double displacement reactions or metathesis reactions. We get H2CO3, since hydrogen has a positive 1 charge and carbonate negative 2 charge. We need 2 hydrogens for 1 carbonate. And calcium chloride, CaCl2. CaCl2. But that's not the end of it, because H2CO3, carbonic acid, is not a very stable acid. So the carbonic acid will actually then decompose to form H2O and CO2. So H2CO3 will decompose to form H2O and CO2. Oh, this is the reverse of forming an acid. An acid can dissociate into a nonmetal oxide in water. Nonmetal oxide, carbon's a nonmetal, carbon dioxide, therefore, is a nonmetal oxide, and water. So there you go. So carbonic acid, later on we'll see, much later on when we learn about equilibrium, why this is the case. We'll see why equilibrium favors that the carbonic acid mostly, if not entirely, dissociates into this. But yeah, the carbon dioxide then, if you were to perform this reaction in the lab, you would actually see it coming out. You would see bubbles coming out, which is why the reaction of calcium carbonate and, in fact, other metal carbonates, or not even carbonates, just anything involving metals, with acids will give you what are called gas-forming reactions. So I'm going to write the whole reaction again, calcium carbonate plus HCl, and this time maybe we'll actually balance it. I forgot to do that earlier. But calcium carbonate plus HCl gives us the final products are calcium chloride and H2O and CO2, which rises as a gas. So this is sometimes called a gas-forming reaction. Gas-forming reaction. Okay, balancing, so we have, I guess we just need 2 here, and I think that solves it. 2 chlorines, 2 chlorines, 2 hydrogens, 2 hydrogens, 3 oxygens, 3 oxygens, 1 carbon, 1 carbon, 1 calcium, 1 calcium. Yep. And I guess we can do the same thing up there. And there we go. Everything is all balanced. Now let's take a look at just the reaction of a pure metal with an acid. So let's grab a new sheet. Let's say I wanted to react, I don't know, let's do magnesium. Let's say I wanted to react magnesium with, let's do sulfuric acid this time, H2SO4. Okay, so again, a gas is going to form here, because what we're going to end up with is the magnesium will pair up with the sulfate ion, so we get magnesium sulfate. And then the hydrogen just gets kicked out as a gas. Maybe I should actually label the phases here. This will be aqueous. Sulfates are soluble with the exception of, let me go back to our solubility rules. Sulfates are soluble except with lead 2, calcium, strontium, mercury 1, and barium. Okay. The rule for sulfates I tend to forget pretty often. But yeah, so sulfuric acid, that would be aqueous, and magnesium here would be in the solid state. And come to think of it, we can actually write some net and total ionic equations here. So let's go ahead and do that. Let's go back to this reaction and try to write the total ionic equation. So I'm going to copy it over first of all. So we've got solid calcium carbonate, doesn't dissolve in water. If we react it with 2 hydrochloric acid, which is aqueous, then we get, let's see, calcium chloride, which is in the aqueous form, plus water, which is in the liquid state, plus carbon dioxide gas. Okay, if we write the total ionic equation for this, calcium carbonate is solid, it does not dissociate, so it stays as calcium carbonate. Hydrochloric acid, we get 2 hydrogen ions and 2 chloride ions. Calcium chloride, we get a calcium ion and 2 chloride ions. And of course water and carbon dioxide stay as is, H2O liquid and CO2 gas. Okay, and if we look for our spectator ions, there's only one, which is the chloride ion. Chloride is the spectator ion, it shows up on both sides, so the net ionic equation is just calcium carbonate plus 2 of the hydrogen ion gives us the calcium ion plus H2O and CO2 plus water and carbon dioxide. Okay, so that's with calcium carbonate, and other carbonates will follow a similar pattern, of course. Let's take a look at the reaction we have up here and write its total ionic equation. So magnesium will stay as a solid, it doesn't dissociate. H2SO4, sulfuric acid, so sulfates are soluble with a couple of exceptions. Hydrogen is not one of those exceptions. So that separates into 2 hydrogens and 1 sulfate. Then we get magnesium sulfate, which is in the aqueous phase, so magnesium ion plus sulfate ion plus hydrogen gas. And our spectator ion in this case is just the sulfate ion. Just the sulfate ion. So our net ionic equation would be magnesium solid plus 2 aqueous hydrogen ions yields magnesium ion plus hydrogen gas. That's the summary of the reaction that goes there. So those are the reactions of acids with metals and also with metal carbonates. And those are just the main ones that chemists are concerned with. Those are the ones that were worth mentioning in my book. They don't mention anything about the reactions of nonmetals with bases, because I guess they don't consider it to be important enough or interesting enough. But yeah, let me think about it for a second. Is there anything interesting I could do between a nonmetal and a base? Let's see, nonmetal with a base. So if I did something like, say, nitrogen with sodium hydroxide, would there be anything interesting going on there? Nothing of note comes to mind, but if I think of something, maybe I'll mention it in a pinned comment. Let's take a look at the reactions of acids and bases with each other. Let's go ahead and take a look at what happens when acids and bases react with each other. So let's take, how about, well, let's do the classic sodium hydroxide plus hydrochloric acid. Let's do that one. So when a base reacts with an acid, we always get a salt with water. So base plus acid always gives us a salt and water. And when I say salt, I don't necessarily mean table salt. Remember, in chemistry, salt refers to any ionic compound. Ionic compounds are also called salts. So sodium hydroxide plus hydrochloric acid, that would give us sodium chloride, that's our salt, and water. And this equation is perfectly balanced. Total numbers of hydrogens are equal. We didn't do anything with the sodium or the chlorine or the oxygen, so we're good. Okay, so these should be in the aqueous phase. Same thing with table salt. And then H2O is the liquid that forms. And if we try to write the total ionic equation for this, then we're going to get sodium ion plus hydroxide ion, both in the aqueous phase, plus hydrogen ion plus chloride ion yields sodium ion plus chloride ion plus H2O liquid. Liquid and then parentheses. I don't even know if that's readable. The parentheses are a little too close to the L. Okay, spectator ions. We've got sodium and we've got chloride. This is always going to be the case whenever you react an acid with a base. The net ionic equation is, I'll write cations first and then anions. That's the way I prefer to do it, and I think that's the way most chemists prefer to do it. Hydrogen ion, then hydroxide ion, gives us water. This is always going to be the net ionic equation for a reaction between an acid and a base. Speaking of which, this kind of reaction is called an acid-base neutralization. Where should I write it? I guess I'll write it here. An acid-base neutralization reaction. And it's called neutralization because as long as you have just the right amount of base and acid such that there are no leftovers for the base or for the acid, so when neither of them is an excess reactant, then what you should end up with is a solution that is neutral when it comes to acidity or basicity. You should end up with something that is neither acidic nor basic, but just some natural, or I shouldn't say natural, but some solution of a salt, a normal salt solution. So that's why they're called acid-base neutralization reactions, because they overall reduce the basicity or acidity, and if you use just the right amounts, they will completely neutralize any acidity or basicity that a solution may have had before the reaction started. Okay, let's take a look at another one. So let's do H2SO4, and I'm going to skip on writing the phases here. Let's do H2SO4 with, how about, how about potassium hydroxide? H2SO4 with KOH. So that should give us K2SO4 plus H2O, and if I try to balance this, then I'm going to have a 2 here, and I think that, no, and a 2 there. Okay, that balances everything. So we've got 2 hydrogens plus 2 times 1 is 4 there, 2 times 2 is 4 there. 1 sulfate, 2 potassium, 2 potassium. Let me see, and I guess that 1 oxygen, or no, 2 times 1 oxygen and 2 times 1 oxygen there. The oxygens in the sulfate were already accounted for. Okay. Total ionic equation, so we've got 2 hydrogen ion plus sulfate ion plus 2 potassium ion plus 2 hydroxide ion. You can check with the solubility rules to confirm that both of these substances are indeed soluble. And what we're left with is 2 potassium ions and 1 sulfate ion and 2 waters. Okay, spectator ions are the potassium ion and the sulfate ion. And so our net ionic equation, we've got, you would think it's 2 hydrogen plus 2 hydroxide gives us 2 water, But this isn't correct because the balancing coefficients all have a common factor. Right? 2 and 2 and 2, that isn't how you balance equations. You go for the simplest whole numbers required. So if I reduce everything by 2, it ends up as just being H plus OH minus gives us H2O, same as what we had up here. And of course you can mess around with other acid-base neutralizations and confirm for yourself that every time you react a base with an acid, you do get an ionic compound plus water, and this is always the net ionic equation for an acid-base neutralization. It's always hydrogen plus hydroxide gives you water. Okay, I think with that we've covered enough content to go back to the problem that we skipped last time that involved an acid and a base. So let's go ahead and look at that. It was problem number 54, and it said, in an accident, a solution containing 2.5 kilograms of nitric acid was spilled. 2 kilograms of sodium carbonate was quickly spread on the area, and carbon dioxide was released by the reaction. Was sufficient sodium carbonate used to neutralize all of the acid? So in this case, sodium carbonate is not a base, but that's okay. You can still neutralize the acid in the sense that you can get rid of the hydrogen ions that the acid supplies. That's what makes it an acid in the first place. So let me go ahead and copy down that information, and then we can start working on a solution. So we have 2.5 kilograms of nitric acid. Notice they did not give us the formula. Better know your nomenclature. Nitric acid is HNO3. 2 kilograms of sodium carbonate was quickly spread on the area, and they just said the word 2. They didn't give us the number of sig figs, so I guess you can assume an infinite number of sig figs. So you can say exactly 2 kilograms, even though it's unrealistic because, I mean, who can measure out exactly 2 kilograms of sodium carbonate to pour onto some nitric acid that was spilled? But, you know, if they write the word to TWO, then we can't really make any other assumption about the number of sig figs. Let's see. And the question was, did we use a sufficient amount of sodium carbonate to neutralize the acid? Well, let's write out the reaction first. So this is going to be another one of those gas-forming reactions. So we've got HNO3 reacts with sodium carbonate. And I've already seen what happens when acids react with carbonates. We get, let me see. So we get the salt, which is going to be sodium nitrate, and I probably should have left some space there for a balancing coefficient. And we also get carbonic acid, but carbonic acid will dissociate into water and carbon dioxide. This is something that you just have to know. Okay, let's go ahead and balance this. So it looks like I'm going to need a 2 here and a 2 here. And I think that does it. 2 sodium, 2 sodium, 2 nitrate, 2 nitrate, 2 hydrogen, 2 hydrogen. Let's see. As for the non-nitrate oxygens, we've got 3 here and we've got 3 there, so that's good, and 1 carbon, 1 carbon. Okay, we're good to go. Let's figure out the molar masses of these guys. So I'm going to pull up my periodic table. Let's see. So we have nitric acid is nitrogen 1.008 plus nitrogen 14.007 plus 3 oxygen, that's 3 times 15.999. Nitric acid is 63.012. And you can't see that on the screen, can you? Let me switch back to that. Don't want to make the same mistake as last time and go on for whatever it was, 10 minutes, writing on a paper that you can't see. Sodium carbonate, so we've got 22.990, 2 of that, so 2 times 22.990 plus carbon is 12.011 plus 3 oxygen, 3 times 15.999 gives us 105.998, or no, 988 grams per mole. Okay, let's figure this out. So this is a limiting reactant problem. They were asking if we used enough sodium carbonate to completely neutralize all of the nitric acid that was spilled. So, of course, like we covered last time, there's 2 different ways to determine what the limiting reactant is. One method is to just calculate how much of one of the reactants is required to completely react with the other, and based on that, figure out which one we have more of. The other method is to pick one of your products and calculate the amount of that product based on both of the reactants and see which one gives you less product. I'm going to use that first method since it's what I prefer. To me, it's just much more intuitive and it's less paperwork as well. So I'm going to say 2.5 kilograms of HNO3. I'm going to figure out how much sodium carbonate is required to react with all this. So first I need to convert my kilograms to grams. And notice that I've stopped including the names of the compounds here. Every 1 kilogram is 1,000 grams. Okay, and then for every, we're talking about the nitric acid here, so 63.012 grams of nitric acid gives us 1 mole. And then every 2 moles of nitric acid gives us 1 mole of sodium carbonate needed to react with it. And then every 1 mole of sodium carbonate is 105.988 grams. Almost wrote moles there. And then, of course, convert the grams back to kilograms. So every 1,000 grams equals 1 kilogram. In fact, we can just cancel these 2 steps out with each other. Right? They cancel each other out. They're basically the reverse of each other. Let's see. So 2.5 times 1 over 63.02 times 1 over 63.02, or no, 63.012, my bad, is 0.039, or no, 0.040 if we round it to 2 sig figs. So 0.040 moles so far, and that's of nitric acid. Then here we convert to moles of sodium carbonate, so it's just times 1 over 2, that's going to be 0.020. Now we've got moles of sodium carbonate, and multiply that, well, actually, I guess it would be kilomoles. No, it would be moles. It would be moles. Okay, so 2.5. Oh, we already did that one. What am I even looking at? So we've got 0.020 times 105.988, and that gives us 2.1. That gives us 2.1 kilograms of sodium carbonate required. If we only pour on 2 kilograms of sodium carbonate when we need 2.1 to completely react with the acid we have, then that means that we have not used enough sodium carbonate. We came close, but not close enough. We're off by 0.1 kilograms. So yes, the limiting reactant is the sodium carbonate. We're going to have an excess of nitric acid. Some nitric acid will still remain unreacted due to insufficient sodium carbonate. Okay, so there's that problem out of the way. Let's take a look at some other problems involving acids and bases. I think I have other acid-base. Oh, no. Those acid-base problems are for later. Okay, so I guess the next thing I want to do then is talk about oxidation and reduction. New topic. Time to talk about oxidation and reduction, and maybe I should start this on a new page. Oxidation and reduction. Or if you prefer, reduction and oxidation, sometimes abbreviated as redox. Sometimes abbreviated as redox. Often abbreviated as redox. So what is oxidation? What is reduction? You might think oxidation is reacting with oxygen, and technically a lot of things that react with oxygen, if not anything that reacts with oxygen, does indeed get oxidized, but oxidation is much more general than that. Oxidation is the loss of electrons. Oxidation means losing electrons, the process of losing electrons, while reduction is the exact opposite. It's the process of gaining electrons. Reduction is the process of gaining electrons. So oxidation and reduction go hand in hand. You can't have one without the other. They're two parts of one whole. They're like yin and yang. They have to go together. If something is losing electrons, something else is gaining those electrons, and if something is gaining electrons, it's gaining electrons from something that lost them. So you have to have both at the same time. There's never any process that's just oxidation or just reduction. Instead, what we would call those processes, we would call them a half process, or more specifically a half reaction. We'll see that in a bit. So let's take a look at an example of an oxidation and reduction. So oxidation and reduction reactions are not really their own type of reaction. They're more of a subtype of reaction. If you remember the 5 basic types of reactions that I stated in part 1 of this series, any one of those basic types can also be a redox reaction, or maybe it won't be. Let's take a look at let's take a look at the reaction of magnesium with sulfuric acid. Let's take a look at this reaction. So if we label this based on the 5 different types of reactions that I mentioned in part 1, this would be labeled as a single displacement reaction, because you've got one thing here reacting with a compound, and it's basically replacing one of the ions in that compound. So that would generally be called a single displacement reaction, but it's also a redox reaction. It also involves oxidation and reduction, and we can see that more clearly if we look at the net ionic equation, so that's what I'm going to focus on. Magnesium solid plus 2 hydrogen ion gives us magnesium ion plus hydrogen gas. So magnesium solid plus 2 hydrogen ion gives us magnesium ion plus hydrogen gas. Maybe I should start sipping water more often so that my throat doesn't dry up. I think I'll do that now. Okay. Where was I going with this? Right, so something here lost electrons and something gained them, and if you're paying attention, then you've probably already figured it out. Magnesium had no charge on it originally in its solid form. It was just the raw magnesium metal, and now it's turned into the magnesium ion with a positive charge, so it must have lost electrons. Specifically, it lost 2 electrons. On the other hand, hydrogen seems to have gained electrons because it started with a positive charge and now it has no charge. So we would say that magnesium gets oxidized, and the hydrogen ion gets reduced. And the reason the magnesium ion gets oxidized is because there's a hydrogen ion that can get reduced in its place, and vice versa. So the reason magnesium can lose electrons is because there's something to lose electrons to, and the reason hydrogen can gain electrons is because there's something to gain electrons from. So we can say magnesium is what reduces the hydrogen. We can refer to magnesium as the cause of hydrogen's reduction, and we can call it a reducing agent. We can call it a reducing agent, or sometimes we also call it a reductant. A reductant. And for the hydrogen ion is what causes magnesium to get oxidized, so we can call it an oxidizing agent. We can call it an oxidizing agent or an oxidant. And if you're one of those nutritionally conscious people, the word oxidant might sound familiar because you've probably heard of antioxidants in all sorts of fruits, especially. And yeah, that's something that you'll learn more about if you ever take organic chemistry in college. We will do some organic chemistry at the end of this series, but it's not the same content. It's just going to be a brief introduction to organic chemistry and organic nomenclature. If you want to learn about antioxidants, then you'll actually have to take the dedicated organic chemistry course at the college level. But yeah, so magnesium got oxidized, therefore it's the reducing agent. It caused something to be reduced. Hydrogen got reduced, therefore it must have oxidized something. It is the oxidizing agent. We can split this net ionic equation into a pair of what we call half reactions. I mentioned those a few minutes ago. We can split it into a pair of half reactions. And we call them half reactions because They don't act alone, but it is still useful to look at the two processes as occurring separately. So let's take a look. So the magnesium half reaction, or the oxidation half reaction, let's call it oxidation. So the oxidation of magnesium is going to be, we start with regular magnesium, and it gets oxidized to magnesium ion, producing 2 electrons, which of course are going to go somewhere. So to represent an electron, all you have to do is write a lowercase e with a negative charge. Reduction. For the reduction half reaction, we've got hydrogen ion is going to gain an electron and give us hydrogen gas. So I guess I'm going to need to balance this. We need 2 here and 2 here. No surprise, given that we had 2 hydrogen ions there anyway. Okay, and the half reactions, when you add them together, they should give you the full reaction, or I guess in this case it's a net ionic equation, so maybe not exactly a reaction, but if you add your half equations you should get a full equation, let's put it that way. But of course before you add them you have to be careful about something. In this case the electrons balance out. There are 2 electrons lost here and 2 electrons gained here, so that's perfect. But if these numbers were different, then you would have to multiply each equation in order to get the correct balancing coefficients. And because balancing the electrons is really just a matter of finding the least common multiple, this gives us a very easy way to balance equations that would otherwise be very difficult to balance. We'll see examples of this half reaction method of balancing soon. But yeah, if I were to write this out, then you have magnesium plus 2 hydrogen ion plus the 2 electrons gives you magnesium ion plus hydrogen gas plus the 2 electrons. So I took all of this stuff and I grouped it onto one side of the equation, and I took all of this stuff and I grouped it on the product side of the equation. And there you go. The 2 electrons, they're kind of like spectator ions, except they're not really ions. And so they cancel out. They should cancel out. You should never, ever, ever, ever have excess electrons. Again, never, ever, ever have excess electrons. I think that wasn't enough evers, but hopefully you got the point. Electrons must always cancel out if you try to add a pair of half reactions together to get a full reaction. Okay, now another thing that happens in oxidation reduction reactions is a change in something known as the oxidation number. Oxidation numbers, or oxidation states. Oxidation numbers, or oxidation states, as they're sometimes called. So if I look at something like, I guess we'll just go with the magnesium and hydrogen ion, and the magnesium ion and the hydrogen gas. The solid magnesium would be said to have an oxidation state of 0. The hydrogen gas would also be said to have an oxidation state of 0, which kind of means that they're not carrying charge, except that the association between oxidation numbers and charge isn't really a clear association. We'll see examples that defy that in a couple minutes. And then, of course, we've got magnesium ion, which would have an oxidation number of +2, so I'm going to write +2. I mentioned this before. I think this was in the part 2 of the series. Yeah, I think I mentioned it in part 2. Oxidation numbers, you have the sign before the number. Ionic charge, you've got the number before the charge. If we look at, what's the last thing we have? The hydrogen ion. So hydrogen has a +1 charge, and it has an oxidation state of +1. So far it looks like ionic charge is the same as oxidation number, but again, we'll see examples that kind of fly in the face of that soon enough. Where was I going with this? Right, so the magnesium went from an oxidation state of 0 to an oxidation state of +2. Meanwhile, the hydrogen, it started out as hydrogen ion and turned into hydrogen gas. So the hydrogen went from an oxidation state of +1 to 0. This is another way to define oxidation and reduction. So if an element changes its oxidation state by increasing its oxidation state or its oxidation number, that is a sign of oxidation. If you lose electrons, your oxidation number will go up. If you gain electrons, like the hydrogen did, then your oxidation number will go down. So we can define oxidation and reduction in some new terms. Now we can define oxidation and reduction also as increase in oxidation number, increase in oxidation number, and reduction is a decrease in oxidation number. And now the term reduction suddenly makes a whole lot more sense. It's a reduction in the oxidation number, a decrease in the oxidation number. Now, a common, I wouldn't call it a mistake per se, but a common, what's the word for it? A common pitfall that students fall into when trying to remember which one is which is that students will try to memorize both of these. They'll try to memorize what oxidation looks like and what reduction looks like and what an oxidation half reaction looks like. Something equals something plus electrons, and for a reduction reaction, something plus electrons equals something. A lot of students will try to commit both to memory at the same time, and that'll just help you get mixed up more often. My advice as a beginner, you would want to just memorize one of them and know that the other one is the exact opposite. That would be my advice for beginners. You are better off as a beginner just memorizing one or the other, whichever one makes more sense to you. Okay, so how do we determine oxidation numbers? Oxidation numbers are not just for raw elements or ions. Oxidation numbers can be given to elements in a compound as well. And there are a bunch of rules that we can follow, but really for me it's not about memorizing these rules, it's more about just kind of developing a feel for it. So let me show you a set of rules that we can follow for assigning oxidation numbers. So rule number 1 says oxidation numbers must add up to the charge on the molecule, formula, unit, or ion. We'll see what that means in a minute when I take a look at the oxidation states of all the elements in a polyatomic ion. Rule number 2 says the atoms of free elements always have oxidation numbers of 0. So raw elements that are not part of a compound, that are not ionized, will have oxidation numbers of 0. Rule 3, metals in group 1A, 2A, and aluminum have +1, +2, and +3 oxidation numbers, respectively, when they are part of a compound. So the idea with this hierarchy of rules is that you should apply the rules from rule number 1 and down. So don't apply rule number 3 if it means violating rule number 1. Or I guess in this case, don't apply rule number 3 if it violates rule number 2. Rule 4, hydrogen and fluorine have +1 and -1 oxidation numbers. That's not always true. Hydrogen can sometimes have a -1 charge when paired with metals, but that's technically covered in a later rule here, though not explicitly. Oxygen typically has a -2 oxidation number. There are exceptions for that. There's the peroxide ion and the superoxide ion, which I'll talk about. Actually, let's just talk about it right now. So, oxygen in compounds will usually have a -2 oxidation number unless it's a peroxide. So this is the peroxide ion. For the peroxide ion, the oxidation number of oxygen is -1. You've got 2 oxygens with a total charge of -2, so the oxidation state, the oxidation number for an individual oxygen atom is -1. And when we're looking at oxidation states, we're always concerned with the oxidation state of a single atom. And the other example was the superoxide. So superoxides, the superoxide ion is O2 with a -1 charge. That's called the superoxide ion. So with superoxide, the oxidation number is -1/2, and this is the only case I'm aware of where you actually have a fractional oxidation state. But peroxides and superoxides are rarely encountered. You might come across peroxides every now and then. You almost never see superoxides. But yeah, those are 2 notable exceptions for the oxygen rule. Otherwise, unless oxygen is in its pure elemental form as oxygen gas, the oxygen will have an oxidation state of -2, as Rule 5 would suggest. Rule 6 says that the group 7 elements, those are the halogens, so fluorine, chlorine, bromine, iodine, those will have a -1 oxidation number in compounds. But that's not always going to be the case for chlorine, bromine, and iodine. We'll see exceptions to that. Rule number 7 says that the group 6 elements, the column right next to the halogens, so oxygen, sulfur, selenium, tellurium, and polonium, those will typically have -2 oxidation states. Group 5 elements, nitrogen, phosphorus, arsenic, antimony, those will typically have a -3 oxidation number. And rule number 9 says whenever there's a conflict between any 2 of these rules, apply whichever rule came first in the order that those rules are presented. So I like this set of rules for assigning oxidation numbers more than any other set of rules I've seen in other textbooks, because it's really systematic and it eliminates the guesswork. But eventually you're going to want to just kind of develop a feel for assigning oxidation numbers rather than memorizing these rules. I wouldn't recommend memorizing these rules per se. I would recommend just practicing with them enough that you start to feel the intuition of assigning oxidation numbers. So let's go ahead and look at a couple examples of mine. There are some book examples that I'll get to, but the book examples did not include polyatomic ions, so I would like to cover a couple of those. Let's take a look at the oxalate ion. So that's C2O4 2 minus. Let's take a look at sodium chloride. Let's take a look at let's take a look at ammonia. Let's do potassium hydride. Let's do the hydrochloric acid. Let's do hydrochloric acid and the chlorate ion. Or should I? Yeah, let's do the chlorate ion. Let's do the sulfate ion. And let's do the sulfite ion. And let's do the ammonium ion. Okay, there we go. Let's take a look at these and start applying some of those rules that we just covered. Okay, so the first rule in our hierarchy of rules, let me flash back to it real quick, says that the oxidation numbers must add up to the charge on the molecule, formula unit, or ion. So whatever oxidation numbers I assign here, they better add up to -2 in the end when you account for each and every atom of a given element. So I would start with the oxygen rule. Oxalate is not a peroxide or a superoxide. So in this case, oxygen ought to be -2. An individual oxygen atom, in this case, would have a -2 oxidation state. It's not in its raw elemental form. It's part of a polyatomic ion. So in this case, oxygen should be -2. And I've got 4 of those oxygens. So if I've got 4 -2s, that's a total of -8 so far. And I have 2 carbons, whatever their oxidation state is. Once I add them to the -8 coming from my 4 oxygens, I should get a total of -2. So if I've got 4 times -2 is -8, -8 plus whatever the sum of the oxidation numbers are for the 2 carbons should be -2. So that means that the 2 carbons must give me +6. So think of it like this. We've got 2 carbons, so 2 times oxidation state of carbon, plus we've got 4 times oxidation state of oxygen is -2, must equal a total of -2 for the charge of the oxalate ion. So that would mean that carbon has to have a state of +3. If you work out the numbers, if you do the algebra, if I do -8 here, add it to both sides, then I get 2 times oxidation state of carbon is +6, so oxidation state of carbon is +3. Carbon must have a +3 oxidation state per carbon atom. Do not make the mistake of writing +6 here. You've got 2 carbon atoms, each one gets +3. Okay, let's take a look at sodium chloride. So group 1 metals in compounds will typically have a +1 oxidation state, and chlorides will often have a -1 oxidation state. +1 plus -1 is 0, which makes sense because sodium chloride as a whole does not have a total charge on it. So it does make sense that those oxidation states need to add up to 0. Ammonia. So we've got nitrogen and hydrogen. Hydrogen is typically +1 unless it's paired with a metal or paired with itself. If it's paired with itself, then that's just, hydrogen gas, which, as we saw up here, has an oxidation state of 0. But typically, hydrogen should have a positive 1 oxidation state. Since this whole compound is neutral, then that means the sum of the oxidation numbers of all the atoms should be 0. So we've got 3 positive 1s. We need a negative 3 for our nitrogen. That way a negative 3 with 3 positive 1s gives us 0. And again, if you're getting stuck on that math, you can just write it out like this as a sort of algebraic equation. But I think most students are able to just look at it and figure out the numbers with some simple mental arithmetic. Potassium hydride. So if I make hydrogen positive 1 here, the potassium would have to be negative 1. Giving metals a negative oxidation state is not really a good idea. I don't think I've ever seen an example of a metal with a negative oxidation state. So metals have priority in being a positive oxidation state. In this case, potassium is positive 1, forcing the hydrogen to be a negative 1. So that's one of the cases where hydrogen is not positive 1 when paired with metals. The other case, of course, is, again, when it's in pure elemental form. Hydrochloric acid, so hydrogen will be positive 1 here, chlorine, negative 1. Total is 0, which makes sense for a neutral compound. Chlorate ion. So now we get to see an example where chlorine is not going to have an oxidation state of negative 1. And this also applies for bromine and iodine, but not for fluorine. Fluorine is always negative 1, but chlorine, bromine, and iodine can have oxidation states other than negative 1. The 3 oxygens here each have an oxidation state of negative 2. So since we've got 3 of them, that's negative 6 so far. The total charge of the chlorate ion is negative 1, so if we already have negative 6, we need to add 5. We need positive 5 in order to get a total of negative 1. Positive 5 plus 3 times negative 2 equals negative 1. So here, chlorine actually has a positive oxidation state. This would have been the same if I did the bromate ion. This would have been the same if I did the bromate ion, or even the iodate ion. We would have had the same results, negative 2 here, positive 5 here, negative 2 here, positive 5 here. What about the fluorate ion? Well, the fluorate ion does not exist. So fluorine will always, in compounds, have a negative 1 oxidation state. But chlorine, bromine, and iodine will sometimes have positive oxidation states rather than a negative 1. So that's something to be careful about. Sulfate. Again, I'm not looking at a peroxide or superoxide, so oxygen should have an oxidation state of negative 2. It's not a peroxide, superoxide, or pure oxygen gas. I keep forgetting to mention the raw elemental form. But yeah, so we've got negative 2 for oxygen. It's a pretty reliable rule. It's correct, I'd say, over 90% of the time. Sulfur then would have to be positive 6. And you can check my math. Negative 2 times 4 is negative 8. And 1 times positive 6 is 6. So negative 8 and positive 6 is negative 2, which is the total charge of the sulfate ion. Sulfite ion, so we've got 3 oxygens this time, each with an oxidation state of negative 2. We've got 1 sulfur that's going to have an oxidation state of positive 4. And there we go. That's the sulfite ion, positive 4 plus 3 times negative 2 gives us a total charge of negative 2. Ammonium ion. The hydrogens are typically positive 1 unless it's elemental hydrogen or paired with a metal. So we've got 4 positive 1s, which means nitrogen here is going to have to be a negative 3. And you might be wondering, this is our second example with nitrogen. Is nitrogen always a negative 3? Nope. Just like with chlorine and bromine and iodine, nitrogen can sometimes have positive oxidation states as well. So an example of that would be the nitrate ion. And I know you're probably getting tired of examples by now, but we still have more to go. So if I look at my nitrate ion, we've got 3 oxygens with negative 2 each. The single nitrogen would have to be a positive 5. Positive 5 plus 3 times negative 2 gives us the negative 1 charge of the nitrate ion. Okay, now let's take a look at some book examples. So let me open that up. Okay, and let's look over here. So it says determine the oxidation state of the elements in the following compounds. We don't have to do all of them, but let's look around and see what we can figure out. So sodium iodide. What's GD? I don't think I've ever seen. Gadolinium. Gadolinium. Interesting. I don't think I've ever encountered gadolinium before. I mean, I know it's always been there on the periodic table, but I've never actually had a problem involving gadolinium. We've got lithium nitrate, we've got, it looks like, what would I call that? I would call that dihydrogen selenide, since selenium is a nonmetal. Mg2Si, I would call that magnesium silicide, I guess. And we've got rubidium superoxide, RbO2. Yeah, rubidium can only form a positive 1 charge, so the O2 must be a negative 1. So even if they didn't spell it out for us, that is a superoxide right there. And we've got hydrofluoric acid. Let's do dihydrogen selenide, or dihydrogen monoselenide, I should say. You need mono for the second element. So let's do dihydrogen monoselenide. Let's do lithium nitrate, the one that was just above it. And let's do magnesium silicide, rubidium superoxide. Let's do each of those. Okay, so we've got dihydrogen monoselenide. That's going to be, hydrogen is a positive 1, since it's not paired with a metal, which means the selenide, or the selenium rather, should have an oxidation state of negative 2. 2 positive 1s and a negative 2 is 0. All of these, by the way, are neutral compounds, so they're going to have to add up to 0. Lithium nitrate, so if we look at the nitrate ion as a whole, the nitrate ion as a whole is going to have a total of negative 1. And since lithium nitrate as a whole is going to have a total of 0, since lithium nitrate as a whole needs a total of 0, the lithium must be a positive 1, so that takes care of the lithium. Now if we zoom into the nitrate, we already did nitrate earlier. Oxygen is negative 2, nitrogen is positive 5. So oxygen negative 2, nitrogen positive 5. So anytime you're dealing with an ionic compound that involves polyatomic ions, look at the polyatomic ions individually before figuring out any of the other oxidation numbers. Magnesium silicide, so magnesium would have to be a positive 2, and the silicide would have to be a negative 4. So for ionic compounds, if the ions are not polyatomic ions, then the oxidation state equals the ionic charge. Unless the ions are polyatomic, ionic charge can be the same as oxidation state. So that's the one and only case where the ionic charge equals the oxidation state, when it's monatomic. Rubidium superoxide, that's what this was. So rubidium is going to have to be positive 1, and superoxide is negative 1 as a whole, which means negative 1/2 for each oxygen in it. Okay, so that takes care of those. Let me take a look at this other set of examples and see if there's anything in there we're going to want to look at. Number 17, I'm liking aluminum hydroxide, selenium dioxide, potassium nitrite. Okay, so B through F for number 17. And for number 18, actually, I like all of these. Let's do all of them. I'm going to do all of them, so let's copy them down one by one and work them as we go. And of course, if you've already got the hang of this, then you can feel free to skip this part of the video. I wouldn't blame you, but for those who need to see more examples, this is for you. Phosphoric acid, H3PO4. I'm going to run through these a little bit more quickly. So we've got oxygen is in the -2 state, as it usually is. The phosphate ion has a -3 charge overall. So if I've got 4 oxygens giving us a total of -8, phosphorus would have to be a +5 so that we can get a -3 for phosphate as a whole. Hydrogen is going to be +1 then. 3 1s plus a 5 is 8, and then plus 4 -2s is a 0. Okay, aluminum hydroxide. Aluminum hydroxide. So hydroxide ion should total to -1. Hydrogen is +1. It's not paired with a metal. Oxygen is typically -2, and this is no exception here. -2 and 1 is -1 for hydroxide. And aluminum would have to be +3, since we've got 3 hydroxides, each with -1. Okay, next we've got selenium oxide. Or selenium dioxide, I should say, because selenium is a nonmetal. This is not an ionic compound. So we've got -2 for oxygen, as we typically get, and selenium would have to be a +4 then. Selenium would have to be a +4. Actually, wait. Oh, yeah, they say none of the oxygen-containing compounds are peroxides or superoxides in the problem itself. Let me flash that real quick. Okay, so, yeah. For a minute there, I was thinking it might be selenium peroxide, but it's not. Okay, next up we've got potassium nitrite. So, KNO2. Let's see. So, potassium nitrite, potassium ion is a monatomic ion, so its ionic charge of +1 equals its oxidation state. Nitrite has a total of -1. So that means that since the oxygen is -2 and we've got 2 of them, the nitrogen has to be +3. positive 3 with 2 negative 2's is a negative 1, and then plus the 1 from potassium is a neutral compound. Okay, next up we've got indium sulfide. Is indium? Yes, indium is a metal. So indium sulfide. Indium sulfide, In2S3. So in this case, since it's an ionic compound and each of the ions are monatomic, we can just use the ionic charge. Sulfide ion is -2, which leaves indium to be +3. And I guess you could have predicted indium would be +3 since it's in the same column as aluminum and gallium. Okay, next up we have tetraphosphorus hexoxide. So oxygen, typically a -2. We've got 6 of those, so -12. For a neutral compound, we're going to need another +12 over 4 phosphorus atoms, so each one must carry a +3 oxidation state. Okay, next up, H2SO4. I think we already did that one. Did we? Well, we did the sulfate ion, and yeah, it's not too different. Calcium hydroxide, we already did aluminum hydroxide. Oh, BROH. Interesting. BROH. Bromine hydroxide? I don't think that's the case, but just follow the rules. So hydrogen, unless it's paired with a metal, would be a +1 oxidation state, or if it's in elemental form. Oxygen is typically -2, unless it's a peroxide or superoxide or pure elemental oxygen, which is not the case here. And that leaves bromine to be, I guess, +1. Interesting. Unless, okay, so the way I would have written this, I know what this is. This is hypobromous acid. I would have written it as HBRO, where BRO is the hypobromite ion, which has a total charge of -1. Okay, that's why it was bugging me. Let's see, we've got ClNO2. This is another strange one. ClNO2. So oxygen would be in a -2 state. Nitrogen, I'm not sure yet, actually. This one's interesting. So we've got chlorine, nitrogen, and 2 oxygens here. There are a couple of different ways this could go. Nitrogen can be -3, which would make the chlorine +5. We could also have chlorine being -1, making the nitrogen a +3. Yeah, this one's a bit unclear. This one is not so clear. Well, let's go look at our rule hierarchy and figure out what takes priority. So we've got, okay, group 7 elements having a -1 oxidation state comes before group 5 elements having a -3. So then I guess chlorine will be the -1, making nitrogen a +3. Okay, so this is one of those rare cases where having the rules memorized can save you, but for the most part, you can do these after just developing a little bit of intuition. The only things you really need to remember to get through most of these is that oxygen typically carries a -2 charge, while hydrogen, or sorry, not a -2 charge, a -2 oxidation state, while hydrogen typically carries a +1 oxidation state unless paired with a metal. So let me see, that takes care of that strange compound. What would I even call this thing? I'm not entirely sure. Maybe I'm just looking at it wrong. Anyway, let's not get too bogged down in the details. The next one is TiCl4. So that's going to be titanium 4 chloride. Metal with nonmetal is always an ionic compound, so TiCl4. The chloride ion is -1, and we've got 4 of them, so titanium should have a +4 oxidation state. And finally, sodium hydride. Again, this is one of those cases where hydrogen is not going to have a +1 oxidation state because sodium has to have the +1 oxidation state. And there we go, all done with oxidation numbers. Now let's talk a little bit about chemical reactivity. Let's talk about chemical reactivity. So sometimes, especially when we're talking about single displacement reactions, or probably exclusively for single displacement reactions, it's not always a simple matter of putting one raw element in with a compound and expecting something to be substituted. So, for example, if I dip a piece of silver into some copper 2 nitrate, so that's CuNO3 2 in the aqueous phase. If I dip some solid silver into copper 2 nitrate, I don't necessarily get a single displacement. I don't necessarily get silver nitrate plus metallic copper. All nitrates are soluble, so that would be aqueous. Copper would deposit as a solid if this reaction were to actually go. But how do we know whether or not this reaction will actually proceed? So, another interesting thing that we encounter when it comes to oxidation and reduction is that different elements have different reduction potentials and different oxidation potentials. We'll talk about oxidation and reduction potentials in more detail when we cover the electrochemistry chapter. But for now, you can think of oxidation potential as the tendency to get oxidized, while reduction potential is the tendency to get reduced. And anything that has a high tendency to get oxidized is going to have a low tendency to get reduced, and vice versa. So oxidation potential and reduction potential, you could say, are inversely related. When one goes up, the other goes down. So when we're talking about metals specifically, metals typically get oxidized. Metals typically lose electrons, especially raw metals. If the metals already have some positive oxidation number, they can get reduced, of course, but you can't reduce them down to a negative, so if their oxidation number starts as 0, most metals will want to get oxidized, not reduced. So when we compare the silver metal here to the copper metal here, depending on their difference in oxidation potential, we can determine whether or not the silver is going to want to exist in its oxidized state. Here its oxidation number is 0, while here its oxidation number is +1, or whether the copper prefers to be in its oxidized state more strongly. So here it would be a +2, while here it's a 0. So, of course, the only way to figure this out is to just do the experiments in the lab and just kind of record the results and compare different pairs of metals to see what works. And in fact, after doing that comparison, we end up with something like this. Let me rotate the camera so you can see it better. So we end up with this thing right here, which is the activity series, or reactivity series as it's sometimes called. So the higher up you are on this activity series, the greater the likelihood that you're going to exist in the oxidized state with some sort of positive oxidation number rather than existing as a raw metal with 0 for your oxidation number. So if I compare silver and copper, copper has more chemical reactivity than silver. It's got a greater oxidation potential. It has a greater desire to be oxidized than silver does. So if we pit copper and silver against each other and only one of them gets to form positive ions, only one of them gets to have a positive oxidation state, then copper is going to come out as the winner. You don't really have to memorize this, you just have to understand how to use it. But yeah, that's the activity series for metals. So if we go back and look at the reaction I just proposed, this reaction would not happen. Let me rotate the camera back. Does that look right, or is it off? Okay, there we go. So this reaction is going to be a no. This reaction does not happen. If you dip a piece of silver into a copper 2 nitrate solution, nothing is going to happen. Silver has less chemical activity than copper does, so copper is going to be more likely to exist as part of a compound than as a raw metal. It's not going to yield its place to the silver. It's not going to give up its seat, so to speak. Isn't that how it works in the lunchroom? I don't know how high school lunchrooms work nowadays, but I would imagine the tougher students, unless they have assigned seats in the cafeteria, will be less likely to give up their seats to the not-so-tough students. And if they want a seat that's already occupied by a not-so-tough student, then I suppose they can just, force the not-so-tough student out of their seat. But now our analogies are starting to get a little dark. Let's take a look at some example problems working with chemical reactivity real quick. And for this, you might want to go back to when I had the activity series up and pause that part of the video and take a screenshot or something if you want to follow along. Otherwise, you can just take my word for it. So these are a couple of problems that I pulled from the, I don't even know how to pronounce it, Chemistry Libra Texts, I think it's pronounced. But yeah, it's a website. I think it's like chem.libretext.org or something like that. Just go to Google and type chemistry, Libre texts, and you'll find these problems along with a whole bunch of others. Anyway, it says, using the activity series for the first question, what happens in each situation? If a reaction occurs, write the net ionic equation, then write the complete ionic equation for the reaction. So they want you to write the net ionic equation first. Interesting. So first we've got platinum wire is dipped in hydrochloric acid. Platinum wire is dipped in hydrochloric acid. So if I look at my activity series and I compare platinum with hydrogen, right? Because if platinum replaces hydrogen, you're going to get hydrogen gas and platinum chloride. Maybe I should write out the reaction for you guys to look at. Let's go ahead and do that. Let's switch to camera. So basically we're asking platinum plus hydrochloric acid, do we get platinum chloride? I don't even know what the charge on platinum would be. Probably a +2. Okay, I'm just going to guess +2 and say PtCl2, so platinum 2 chloride. Your guess is as good as mine whether or not that's actually what you get. But yeah, the question is this a go? And of course, if we look at our activity series, which I showed a couple minutes ago, I see platinum is the second to last one at the bottom. Hydrogen is 4 steps above it, so hydrogen is not going to give up its place with the chloride ion. Hydrogen wants to stay in its oxidized state more than platinum wants to get into an oxidized state. So hydrochloric acid stays as hydrochloric acid, and platinum stays as platinum. So no reaction. No reaction. Okay, let's read the next one. So the next one says manganese metal is added to a solution of iron 2 chloride. Manganese metal, iron 2 chloride. So it's manganese versus iron. Manganese versus iron 2 chloride, FeCl2. Will we get, and again manganese is a transition metal, I'm going to guess if it develops a charge, it'll develop a charge of +2, but again your guess is as good as mine. You're not expected to know this stuff. Predicting the charges of transition metals is kind of a tall order. So the question is, does this happen? Looking at my activity series, manganese is above iron in the chemical reactivity series. It's got a greater oxidation potential. Its desire to be oxidized is greater than iron's desire to be oxidized. So the manganese will get oxidized. It goes from an oxidation state of 0 to, I'm guessing, an oxidation state of 2, while iron goes from an oxidation state of 2 to an oxidation state of 0. So manganese gets oxidized, iron gets reduced. A reaction does happen here. They wanted the net ionic equation for this, and the net ionic equation is, well, the chloride is going to be the spectator ion here. If you've practiced enough with total ionic and net ionic equations, maybe you can already see that immediately. If you can't, you may want to practice some more. It's not one of those skills that teachers emphasize, but it is a skill that definitely comes in handy once you've picked it up. It'll save you a lot of time, especially on the AP exam, if you're taking the AP exam, where they want you, for the free response section, to report all of your answers to reaction questions as net ionic equations. Anyway, I'm rambling too much. Manganese plus iron ion, the iron 2 ion to be specific, becomes the manganese 2 ion, presumably, plus solid iron. There's your net ionic equation. The total ionic would be pretty much the same thing, except there would be +2 chloride here and +2 chloride here, which would, of course, cancel out on both sides. Let's see. we've got tin is heated with steam is the next one. So we're comparing tin with hydrogen. Wait a minute. No, steam is not hydrogen, it's water. So we're comparing tin with hydrogen and figuring out which one gets to be paired up with oxygen. So tin is above hydrogen in chemical activity. Tin is above hydrogen in chemical activity, so when tin interacts with H2O, we will indeed get, let's see, tin is, your guess is as good as mine as to what charge it develops. I'm going to go with +2, since that's typical for a lot of transition metals. So I'm going to say tin 2 oxide plus hydrogen gas. And that doesn't need any balancing. So we're good to go. Speaking of balancing, I should have balanced this one earlier. Not that a reaction actually occurs, but, you know, it's good to get in the habit of balancing all your equations so that you can never forget the skill of balancing. Tin, water, tin oxide, hydrogen. So net ionic equation. In this case, this is the net ionic equation. This is the net ionic equation because the tin is in solid form. They said the water was in the form of steam. Here you've got hydrogen gas, and here you've got tin oxide, which I suppose... I suppose this is going to exist in solid form, actually. But you could also argue that this is aqueous. Even if you did, it doesn't matter. There aren't any ions that show up on both sides of the equation that we could cancel out as spectator ions. So this is the net ionic equation. Okay, and let's do one more, and you can look at those other four for yourself if you want additional practice. D for the first question says hydrogen gas is bubbled through a solution of lead to nitrate. Hydrogen bubbled through lead to nitrate. So hydrogen versus lead is what we're looking at. Hydrogen gas versus lead to nitrate. Will we get, I guess this would form nitric acid plus elemental lead. And to balance, I would need a 2 here. Okay, let's see. So looking at my activity series, lead is just above hydrogen. Lead is just above hydrogen in chemical reactivity. Lead is not going to give up its place with the nitrate ion to hydrogen, so no reaction occurs here. Nothing happens. Okay, and that's the basics of chemical activity. Let's see what else I have lined up for you guys. So now we go back to some more redox. Let's practice identifying, oxidizing, and reducing agents. I kind of did this already when I was looking at the oxidation numbers and how they changed over here for the manganese and the iron. So to determine whether or not redox is happening, all you have to do is look at an element on one side of the equation and look at that same element on the other side of the equation and see whether or not its oxidation number went up or went down. If its oxidation number went up, then that means the element was oxidized. If it goes down, that means it was reduced. So that's how you identify oxidation and reduction when it's happening in equations. let's take a look at some of those. So we've got magnesium plus nickel 2 chloride is our first example. Gives us magnesium chloride and solid nickel. So, of course, we can assume from this that magnesium has more chemical activity than nickel. But yeah, identifying the what do they want us to do? It says identify the atoms that are oxidized and reduced, the change in oxidation state for each, and the oxidizing and reducing agents in each of the following equations. Okay, let's do a couple of these. And I want to see how I'm doing on time. Looks like we're close to the 2-hour mark at this point. That's actually pretty good progress. Maybe this is not going to be a 5-hour video after all. Magnesium plus nickel 2 chloride. Magnesium plus nickel 2 chloride gives us magnesium chloride plus raw nickel. Okay, so oxidation numbers, we've already practiced quite a bit with identifying oxidation numbers. Raw elements, always oxidation state of 0. Even for the diatomic elements, even your Hofbrinkels. Let's see. So nickel 2 chloride, chloride ion is going to have -1. Nickel 2 ion is going to be +2 here. Chloride ion still -1 there. Magnesium ion is now a +2. And it just so happens to be equal to the ionic charge as well in this case, because these are all monatomic ions. So yeah, magnesium's oxidation state went from 0 to +2. Oxidation number went up. You lost electrons. That's oxidation. Speaking of which, I don't think I gave you the mnemonic for remembering oxidation versus reduction. There's the mnemonic, which is oil rig. Oil rig, which stands for oxidation is loss of electrons, reduction is gain of electrons. Although, personally for me, I like to think of it as reduction reduces the oxidation state. It reduces the oxidation number. To me, that just makes enough sense that I don't even have to memorize it. It's just, you know, it's just there to me. But whatever works for you. Different minds process things differently, so whatever works for you. Magnesium got oxidized, its oxidation number went up. Nickel got reduced, its oxidation number went down from +2 to 0. So both of these elements had their oxidation state change by 2. One went up 2, the other went down 2. Magnesium, since it got oxidized, it must have caused the nickel to be reduced. So magnesium is your reducing agent or your reductant. And that would mean that nickel is your oxidizing agent or your oxidant. And some chemists will just refer to the nickel 2 chloride as a whole as being an oxidant instead, even though it's just the nickel in the nickel 2 chloride that's causing the oxidation, but that's something you'll see, so don't be too weirded out by it. Okay, let's look at another one. Let's do C2H4 plus oxygen gas, so that's a combustion reaction. C2H4 plus 3O2 gives us 2CO2 plus 2H2O. Okay, let's copy that down. So C2H4, that would be ethylene. Plus 3 oxygen gas gives us 2 carbon dioxide and 2 water. 2 carbon dioxide and 2 water. Okay. So oxidation states, oxygen here is a 0, and I guess we've got oxygen in 2 places here, but in both of those places it'll just be a -2. So that's oxygen. Hydrogen is a +1 here and here. It's not paired with a metal or with itself. That leaves carbon, so carbon we've got, let's see, we've got 4 hydrogens here, so that's a total of +4, and 2 carbons there, that's a total of -2. Or not a total of -2, but -2 each. And over here, if I look at carbon dioxide, I've got, unless I've done, wait, is it C2H? Yes, it is C2H4. Interesting. So it looks like we might have multiple things getting oxidized or reduced here. We've got carbon here would have to be a +4. This is rather interesting. Oh, no. It's fine, it's just 2 things. The hydrogen is unchanged. It's between the carbon and the oxygen. Okay, that makes sense. So, carbon got oxidized. Its oxidation number went up from -2 to +4, so it lost 6 electrons, essentially, per carbon atom. So carbon got oxidized, therefore it's the reducing agent or reductant. And oxygen got reduced, therefore it's the oxidizing agent. What a surprise. Oxygen is an oxidizing agent. Who would have thunk it? Yeah, oxygen went from 0 to -2. Okay, that one felt a little weird, but just follow the steps and you'll be fine. Let's take a look at... Oh my goodness. I forget what S2O3 is called. Oh, and I also forget what S4O6 is called. I'm looking at equation E. Let me think. That would be... I think one of them is called metasulfate or metasulfite, but I can't quite remember. Those are some rarely encountered polyatomic ions there. I'll look them up and probably post their names in a comment, but we've got 2 potassium somethingite, or 8. So that's S2O3. And iodine, giving us potassium with S4O6, whatever that polyatomic ion is called, plus 2 potassium iodide. Probably should have looked at these problems ahead of time. I would have thought to look up the names, but it's okay. I'll just post them in a comment or something. Anyway, wait a minute. Do we? Yeah, it's balanced for us. What am I thinking? So if we follow the oxidation numbers, oxygen is typically a -2. We have no reason to believe those are peroxides or superoxides. I think I'm getting a case of the hiccups. Potassium is always in its monatomic ion form, so +1, +1. Potassium is unchanged. Iodine changes from 0 to -1, so that's something. Sulfur must be the other thing that changes. So sulfur here, let's see, S2O3 as a whole is going to have a -2 charge, and I know that because that's the only way you're going to balance your 2 potassium ions. So if it's going to have a -2 charge overall, and you've already got -6 from the 3 oxygens, you're going to need to add 4, so +2 for each sulfur. And then if we go here, this is also going to have a total of -2 for the S4O6. So 6 times -2 is -12. We need to add 10 to get back to -2. Oh, interesting. So 10 over 4, this is +2.5. This is positive, I'm just going to write 2.5. Interesting. I said earlier that peroxide was the only example I've ever seen of a fractional oxidation state, but now I have a second example. I'm suddenly gaining more interest in this rarely encountered polyatomic ion. So sulfur went up from +2 to +2.5. It got oxidized. Therefore, it is the reducing agent or reductant. Iodine got reduced from 0 to -1, so it's the oxidizing agent or the oxidant. And of course, each iodine was reduced by 1, each sulfur was oxidized by 1/2. And there you go. Alright, so earlier I alluded to the idea that we would be using half reactions, oxidation half reactions and reduction half reactions, to come up with an easier way to balance any chemical equations that actually have redox going on. Not all chemical equations will involve oxidation and reduction, but many will. Again, oxidation and reduction, I would call it like a subtype of reaction rather than being its own individual type. Because if we look at each of these, this is a single displacement reaction, this is a combustion reaction, a complete combustion reaction to be more specific, and this is another single displacement reaction. Wait, is it? Actually, what would I call this? So we've got some of the potassium gets paired up with iodine, so iodine kind of takes the place of some of the sulfur. Okay, I would still call this a single displacement reaction, but it's a little bit harder to argue for. I can admit that much. Interesting. But yeah, all of these had oxidation and reduction in them, and yet they still fell into one of the 5 basic types of reactions. But not all reactions have redox going on. In fact, maybe before I start talking about the half reaction method of balancing, I should give an example. Let's go ahead and do that. Let's do... Let us do... Let's do silver nitrate plus sodium chloride gives us silver chloride plus sodium nitrate. So if we follow the oxidation numbers here, we're going to notice nothing changes. Silver is a positive 1 in the beginning and a positive 1 in the end. Chloride is a negative 1 in the beginning and a negative 1 in the end. Sodium is a positive 1 in the beginning and a positive 1 in the end. And nitrate is still going to have a negative 1 charge overall. The oxygens in it are still going to have negative 2. The nitrogen in it is going to have positive 5. So here we notice that no oxidation or reduction occurred, and this is pretty common in double displacement reactions, though I'm pretty sure there are some double displacement reactions that are also redox reactions. I just can't think of any clear-cut example off the top of my head right now. But it is pretty common for double displacement reactions to not have redox going on behind the scenes, because usually all you're doing is swapping the places of the ions. There's no gaining or losing of electrons that's happening. So it does kind of make sense that these exchange or metathesis types of reactions wouldn't often have redox going on. But yeah, if I can think of an example of a double displacement with redox going on, I'll post it somewhere. But for the time being, most, if not all, double displacement reactions usually don't have redox going on in the background. Now then, the half reaction method of balancing chemical equations. Let me go ahead and actually skip over to one of the problems I was going to cover after mentioning this. Let's go ahead and look at part G of problem 40 here. So part G, we've got iron plus iodide ion, the iron 3 ion to be specific, plus the iodide ion becomes the iron 2 ion plus just molecular iodine. Let me go ahead and copy that, and let's figure out how to balance it. You can probably balance it as is without any trouble, but I just want to show the simplest form of the half reaction method. So if we've got Fe3 plus I minus yields Fe2 plus I2, this is clearly not a balanced chemical equation. You could try to balance it just the way we've always done, but it might be helpful to look at a new method. So let's go ahead and do that. Let's split this up into two half reactions. So here they make it pretty easy to determine the oxidation states. Iron is a monatomic ion in both cases. Its oxidation state is equal to its ionic charge. Iodine here is monatomic, so its oxidation state is -1, and this is raw elemental iodine, so 0. Okay, so iron got reduced and iodine got oxidized here. So let's start with the oxidation. So oxidation, you've got I minus becomes I2 plus some electrons. Oxidation half reactions have electrons showing up on the product side. Let's go ahead and balance this. So now we also have to make sure we're balancing charge. So we have to be very, very careful and make sure the charge on both sides is equal, as well as the numbers of the elements on both sides. So I'm just going to need a 2 here to balance the iodines, but now I've got 2 negative charges on the left and 1 negative charge on the right, so I'm going to need to multiply that by 2 as well. So 2 iodines, each one loses a single electron. yielding 2 electrons along with the iodine molecule. Okay, so that's the oxidation half reaction. I'll just say OX for short. And for the reduction half reaction, reduction is when you add electrons to something. So in this case we've got iron plus electrons gives us, well, iron 3 plus electrons gives us iron 2, and this is already balanced in terms of both charge and elements. So we've got 1 iron here and 1 iron there. Positive 3 plus negative 1 is positive 2 on the left, and you've got positive 2 on the right. A lot of students will kind of get hung up on what the charges are on the left and right. You don't have to worry what the charge is. What you have to worry about is making sure that the total charge on the left equals the total charge on the right. What that charge is doesn't matter. It has no effect on the balancing. But anyway, so those are our 2 half reactions, and if I want to add them, you may remember I said earlier you need to get the electrons to cancel out. Never, ever, 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 ever have any free-floating leftover electrons. Never. So I'm going to need the least common multiple of the electrons between here and here, which is easy enough to do. It's just going to be multiplying everything in this equation by 2. And once I've done that, then I can eliminate the electrons. It's kind of like solving equations by elimination in algebra. So if I do that, then I've got 2i minus plus, I guess I probably should have written the iron first, since I prefer to have my cations first. Yeah, let's do that. So just scratch all this, and it looks like this marker is as good as dead. To the trash it goes. And what will be the replacement for this one? Let's go with lime green. Okay, so 2 iron ion plus 2 iodide ion, 2 iron 3 ion, I keep forgetting to say that, plus 2 electrons gives us iron 2 plus molecular iodine plus 2 electrons. You can of course cancel the electrons on both sides, and your balanced equation is 2 Fe3 plus 2 I minus gives us, oh, it's supposed to be 2 Fe2 plus I2. Alright, and there we go. We balanced it using the half reaction method. Could you have just balanced it the normal way we've always been balancing? Sure, if you were careful with your charges and you made sure that they added up correctly, then you could have done that. So if I wanted to do it without the half reaction method, first I'd put a 2 here, and if I did that, then I would balance the iodines, because 2 iodines here and 2 iodines here, but then I would unbalance the charge all of a sudden. We've got 2 negative 1s plus a 3 would give us positive 1 on the left, and on the right we've got positive 2 plus 0. By the way, when I say balance the charge, I'm referring to these, not the oxidation numbers. I guess in this case the oxidation number, since it's a 0. But anyway, yeah, I would start by multiplying this by 2, and then I'd run into a bit of a problem with my ionic charge. I'd have too much charge on the left, it would seem, and wait, is that right? No, too much charge on the right, so I would try to add charge to the left by multiplying that by 2, but now I'd have too much charge on the left, so I would need to multiply that by 2. And yeah, eventually you could balance this without the half reaction method. But the half reaction method can save you considerable time. The half reaction method is almost a necessity when you're balancing redox equations under acidic and basic conditions. So this is something that I usually don't cover until the electrochemistry chapter, where it becomes a necessity, but I have noticed a trend of teachers trying to teach this earlier on in the semester, very early on. And I'm not really sure why, because the earlier you teach it, I feel the more time students have to forget it by the time you actually have to start using it. But oh well, I'll cover it here, and I'll probably cover it again when we get to electrochemistry. So let's take a look at reaction A. It says we've got zinc plus the nitrate ion gives us zinc ion plus nitrogen, and then it says in parentheses, in acid. What does that mean? Well, based on the definition of acids that we started with in this video, we said that acids provide hydrogen ions. So if you're in acid, you have pretty much an excess supply of hydrogen ions that can be used for balancing purposes, and we'll see how that works in a couple minutes. Let's start building this up. So, balancing redox equations, in acids and bases. How do we go about doing it? Let's write that chemical equation that we had for our first example. We had zinc sulfide, or not zinc sulfide, it's zinc solid, but because they put the parentheses right next to zinc, my mind kind of unconsciously reads it as zinc sulfide. I hate that they did that. Zinc solid plus nitrate ion gives us nitrogen gas and zinc ion, so zinc ion positive 2 and nitrogen gas. And you might remember from part 1 of the series that zinc is one of the transition metals that has a well-defined charge, so it doesn't need a Roman numeral. I don't call it the zinc 2 ion, I just call it the zinc ion. Zinc and cadmium have positive 2 99.9% of the time, if not 100% of the time, and silver ion, same thing, but with a positive 1 instead of a positive 2. Anyway, so how do we go about balancing this under acidic or basic conditions? So if this reaction is going on within an acid, then it's inside of presumably water as the solvent, so we have a lot of water molecules available, and among those water molecules we also have a bunch of hydrogen ions that we can use if needed. So let's go ahead and split this into a pair of half reactions. I've got zinc metal will give us the zinc ion. Zinc metal will give us the zinc ion. I haven't determined whether this is oxidation or reduction yet, and I'm not going to worry about that. We'll add in the electrons later. And nitrate, the nitrogen in nitrate somehow becomes nitrogen gas. So we've got some work to do here. Step 1 for balancing a redox equation under acidic or basic conditions after splitting your reaction up into some unbalanced half reactions is to balance anything that is not oxygen or hydrogen. The zincs are balanced, the nitrogens are not balanced, so I'm going to need a 2 here, so now I've balanced my nitrogens. Oxygens and hydrogens we hold off on until the next step. But yeah, the non-oxygens and non-hydrogens have now been balanced. Zinc is balanced, nitrogen is balanced. Next, we balance any oxygens with water if necessary. Every water molecule contains 1 oxygen. So if I have 3 oxygens here and I need 3 oxygens here, then I can get those 3 oxygens by adding 3 water molecules, each one containing a single oxygen. Now, you might notice this creates a new problem. Oh, wait, it's not 3 oxygens. My bad. It's 2 nitrates, so 2 times 3, it's 6. So we need 6 waters. Glad I caught that in time. Okay. So, where was I? So, now we've added some hydrogen. We've balanced the oxygen, but now we've added some hydrogen, which isn't balanced. But we're under acidic conditions, so what we can do is we can have as many hydrogens as we want in the form of hydrogen ions. Let's add, let's see, 6 times 2 is 12 hydrogen ions would be needed over here. And now the oxygens and hydrogens are also balanced. So first balance the non-oxygens and non-hydrogens, then the oxygens with water, then the hydrogens with hydrogen ion. This is still true even if it was under basic conditions, and we'll see why that is once we do this equation again under basic conditions. Now it's finally time to balance the charge. So we've got a charge of 0 on the left-hand side of this half reaction and a charge of 2 here. I can only add electrons. I can't add protons. I can only add electrons. So whichever side has a higher charge will need to have electrons added to it. So I'm going to need to add 2 electrons here. That way positive 2 and 2 negative 1s give us a total of 0, which equals the total charge on the left. For the second half reaction, we've got 12 times positive 1 from the hydrogens, so that's 12 so far, 2 times negative 1 from the nitrates, so that's positive 12, negative 2, that's a total of positive 10. Let's write that down temporarily. And on the right-hand side, we've got a total charge of 0. The nitrogen is neutral and the water is neutral. So it looks like I'm going to need to add 10 electrons over here. So plus 10 electrons on the left-hand side. That way we've subtracted 10 and the charge on the left-hand side, 0, equals the charge on the right-hand side. Okay, let's cross those out so that they don't distract us. So now charge is balanced for each half reaction. Now then, just like we did before, we need to cancel out the electrons. We need to cancel out the electrons. So to do that, I need to find the least common multiple. I've got 10 electrons here and 2 electrons here, so if I just multiply this top equation by 5, I should get a 10 and a 10. Okay, and now combine your half reactions. So we've got 5 zinc plus 12 hydrogen ions plus 2 nitrate ions. I'm not going to write the 10 electrons because I know they're going to cross out. Gives us 5 zinc ion, so 5 zinc ion. I'm not going to write the 10 electrons here either because again they've been canceled out, plus a nitrogen gas plus 6 waters. Alright, congratulations, you have balanced this chemical equation under acidic conditions. Now, what if it's under basic conditions? That's actually the question for part B. It's the same reaction, but now we're doing it. Oh, never mind, it's not the same reaction. Oh well, we'll look at it later. But I want to do the same reaction, so this very same reaction, but now under basic conditions. If you do it under basic conditions, there are only 2 more steps to add. You follow all the same steps that you do for balancing under acidic conditions, but you also add 2 more steps, or maybe just 1 more step, depending on how things work out. You just add 2 more steps. Under basic conditions, so if I were to say, what should I write here? I guess in base, you add the following steps. Under basic conditions, you have, of course, a bunch of water, but also within that water, a bunch of hydroxide ions. Not hydrogen ions, but hydroxide ions. Now, the problem with hydroxide ions is that they contain both oxygen and hydrogen, and since you need to use hydroxides and waters to balance the equation, it can get kind of messy because every time you add water, you're adding more oxygens, which might require more hydroxides to balance the oxygens from that new water, or vice versa. If you add hydroxides, you might need more waters, and that kind of complicates things, but we can take advantage of the fact that if we think back to the net ionic equation from any acid-base neutralization is hydrogen plus hydroxide equals water. We can take advantage of this and think of it as water minus hydrogen ion equals hydroxide. So basically, if you just balance the equation as if it were acidic, that's fine because you can get rid of all of the hydrogens later and turn them into waters by simply combining them with hydroxides. So here's what I'm going to do. I'm going to take this equation that I don't even know what I did here. I'm going to take this equation that we just balanced under acidic conditions, and I'm going to neutralize all the hydrogen ions by adding an equal amount of hydroxide ions. But if I add hydroxide ions to the left-hand side of this equation, I must add an equal number of hydroxide equations to the right-hand side of this equation. Otherwise, I'm going to unbalance it by introducing oxygens that weren't there. So I'm going to add 12 hydroxides here, but I'm also going to add 12 hydroxides here, and I guess I'll just write it up here. Add 12 hydroxides on both sides. That way you're not creating any imbalance in this equation that we worked so hard to balance to begin with. And if we do that, then what you're going to end up with is 5 zinc plus 12 hydroxides and 12 hydrogens combined to form 12 waters, 12 H2Os, plus 2 nitrate, and that's going to give us I wonder if I can fit it all in. 5 zinc ion plus nitrogen gas plus 12 hydroxides. Let's make that O curly, plus 6 water. And I managed to squeeze it all in somehow. Okay, but now I see water on both sides of the equation. That's not the simplest equation I can write. So now that I have water on both sides of the equation, I have one last step, which is to reduce the water. So in this case, we've got 12 waters versus 6 waters here. Take away 6 water on both sides. Take away 6 water on both sides. And if we do that, our final equation, balanced under basic conditions, would be 5 zinc metal plus 6 water plus 2 nitrate yields 5 zinc ion plus nitrogen gas plus 12 hydroxides and no water. And there you go. That's the equation balanced under basic conditions. And that's it. You just follow those steps every single time and you'll be good to go. Even if it doesn't happen under acidic or basic conditions, start off by treating it like acidic, and usually what'll happen if they don't specify that it's under acidic or basic conditions is that it won't matter, because the hydrogen ions or hydroxide ions will simply cancel out. We'll see an example of that soon enough. Speaking of examples, let's look at some of these other problems. So B is very similar to A. I don't think it's worth it to do that one. Let's look at C. Let's take a look at C. So we've got copper 2 sulfide plus the nitrate ion gives us copper ion plus sulfur plus nitrogen monoxide. And it does say in acid, but since it's 2 extra steps anyway, we'll also do it in base. We might as well, if we're going to do all the work that you have to do just to balance it under acidic conditions. Taking the 2 extra steps to balance it under basic conditions is probably worth it. Okie dokie. Let's copy the equation. So copper 2 sulfide plus nitrate ion gives us the copper 2 ion plus sulfur plus nitrogen monoxide. The copper 2 ion plus sulfur plus nitrogen monoxide. Okay. And of course, with that previous reaction, we could have identified the oxidizing agent and the reducing agent and what got oxidized and what got reduced and all that. So you can still do all that, but we've already practiced that, so I don't want to be too excessive with the time I spend on these problems. I want to just focus on the new part. So let's see, split it into half reactions. So copper sulfide, I guess, would give us the copper and the sulfur. It would give us the copper ion and the sulfur ion. Sometimes it can be difficult to decide, you know, what your half reactions should be split into. And sometimes there will be cases where you actually have options and it doesn't matter what option you choose. But typically you want your non-oxygens and non-hydrogens to be in the same half reaction with each other. As for oxygens and hydrogens, you can think of them as your wild cards, since you're going to be balancing them with waters and hydrogen ions and perhaps hydroxide ions anyway. So let's see, we've got balance the non-hydrogens and non-oxygens first. 1 copper, 1 copper, 1 sulfur, 1 sulfur, that's balanced. 1 nitrogen, 1 nitrogen, that's balanced. Okay, step 2, balance any oxygens with water. Let's add, we're gonna need 2 waters here. Again, the number of waters equals the number of oxygens you need to add in order to balance the oxygens, since each water contains 1 oxygen. A lot of students tend to forget that. I don't know why, but they do. Okay, next, balance the hydrogens with hydrogen ions. Yes, even if you're doing it under basic conditions, 2 times 2 hydrogen is 4 hydrogen ion. Now balance charge. So we've got copper sulfide 0 charge, copper 2 ion plus elemental sulfur is positive 2, so I'm going to need 2 electrons here. If I do that, positive 2 and negative 2 is 0, and that side is 0 as well, so it's perfect. Charge is balanced. Over here, 4 times 1 plus 1 times negative 1, so we've got a total of positive 3 charge on the left. On the right, we've got a total of 0 charge, so I'm going to need 3 electrons here. And there we have it. Next, we need to find the least common multiple of the electrons and add the half reactions together. So in this case, least common multiple between 2 and 3 is 6. So I'm going to multiply this by 3 and this by 2, and then I'm going to add those equations together. So let's see what we've got. So that's going to be 3 copper sulfide, 3 times copper 2 sulfide. And that's it for the first half reaction, at least the reactant side. And then over here we've got the electrons are going to cancel out, so I'm not going to bother even writing them. 2 times 4 hydrogen ions, so that's 8 H plus. 2 times 1 nitrate, so that's 2 nitrate ions. And that takes care of reactants. For products, I've got 3 times copper ion, 3 times sulfur, and the 6 electrons that cancel out, so I won't write them. So 3 times 1 copper ion plus 3 times 1 sulfur. So that's the first half reaction. The second one, I've got 2 times 1 nitrogen monoxide and 2 times 2 water, so that's 4 water. And there we go. That is balanced under acidic conditions. What about under basic conditions? Under basic conditions, we would need to cancel out all of the hydrogen ions with an equal amount of hydroxides. So I'm going to add 8 hydroxides here. But if I add them here, then I'm going to have to add them here as well, so that I don't lose the balancedness of my equations, or my equation. I wonder if balancedness is even a word. I guess we'll make it a word if we use it often enough. But yeah, so 8 hydrogen plus 8 hydroxide gives us 8 waters. So we've got 3 copper sulfide, and let me draw a line here so that we don't confuse ourselves. 3 copper sulfide plus 8 water plus 2 nitrate yields 3 copper ion plus 3 sulfur plus 2 nitrogen monoxide plus 8 hydroxide plus 4 water. I see water on both sides of the equation, so we have one last step, which is to take away 4 water on both sides. That eliminates all the water on one side and leaves only the other side with water. So our final balanced equation under basic conditions is 3 copper 2 sulfide plus 8 minus 4 leaves us with 4 water plus 2 nitrates yields 3 copper ion plus 3 sulfur plus 2 nitrogen monoxide plus 8 hydroxide. And there we go. That takes care of another one. So again, if you're balancing an acid, then you stop at this blue equation. If you're balancing in base, you take 2 more steps and stop here. Okay, let's look at another one where it doesn't really specify. So if you look at D, we've got ammonia plus oxygen gives us nitrogen dioxide, and all it says is gas phase. It doesn't say whether it's under acidic conditions or basic conditions, and that's because it's not going to matter. One thing that will matter, though, is that you do have water, so that part will matter. But as long as you remember that part, you might be able to just skip all the steps and directly balance it just using water alone. It is definitely doable, but I'm going to do it the long and hard way first. And then we'll do it the shorter way and see that it leads to the same result. NH3 plus O2. NH3 plus O2 gives us NO2. NH3 plus O2 gives us NO2. Split it into a pair of half reactions. So this part might feel kind of weird. So NH3, of course, has to go with NO2. The non-oxygens and non-hydrogens are the ones that we really want to focus on, but that leaves oxygen here with nothing else to pair it up with. This is completely fine. Never ever worry about what to pair your oxygens and hydrogens with, because you can always add water and hydrogen ions as needed. And that's what I'm going to do for the oxygen, in fact. So for NH3 versus NO2, the nitrogens are balanced, the oxygens are not. I'm going to need 2 water here to balance the 2 oxygens on that side. Over here, I've got oxygen here and nothing here. I'm going to need 2 water to balance the oxygens on the left-hand side. Okay, so far we've added equal amounts of water. Interesting. Next, we need to balance hydrogens. So let me use the yellow marker for this. So I've got 2 times 2 is 4, plus the 3 hydrogens in ammonia is 7 hydrogens, so add 7 hydrogen. That balances hydrogen for us for the first half reaction. For the second one, 2 times 2, I'm going to need 4 hydrogen ion over here. And there we go, that balances the hydrogen in the second half reaction. balance charge. So on the left-hand side of this first half reaction, I've got 0 for my total charge. All of them are neutral compounds. Over here I've got positive 7 from the 7 hydrogens, so I'm going to need to add 7 electrons to make the charge on both sides 0. For the second half reaction, we've got nothing on the right-hand side. We've got positive 4 on the left-hand side, so to make them equal, I'm going to need 4 electrons here. And now we can combine our two half reactions together. Before we can do that, we need to balance the electrons, find the least common multiple between 7 and 4. That would be 28. So I'm going to need to multiply this by 4 and this by 7, and then add. So we've got 4 times 2 is 8 H2O, plus 4 times NH3, let's see, and then plus 7 times 4 electrons. Not going to bother because they're going to cancel out anyway. 7 times 4 hydrogens is going to be 28 hydrogens. Actually, the hydrogens are going to cancel out as well, but let's write them in anyway, just so we can see firsthand what's going on. 7 times O2 is 7 oxygens. That yields 4 times NO2 plus 4 times 7 hydrogens is 28 hydrogens. Plus 7 times 2 water is 14 water. 14 H2O. Alright, and I see 28 hydrogens on both sides. Just like the electrons, these cancel out. And there you go, our final balanced chemical equation. Oh, and let's reduce the water while we're at it. So it looks like I've got 8 water here and 14 water here. Let's subtract 8 H2O on both sides. And that leaves us with no water there. We get 4 NH3 plus 7 O2 yields 4 NO2 plus 14 minus 8 is 6 H2O. And there you go. There are no hydrogen ions and no hydroxide ions in this final equation. It didn't matter if you were going to do it under acidic conditions or basic conditions. The hydrogen ions or hydroxide ions would have canceled out anyway. Okay, now let's just try to balance it straight from the beginning. So the only thing you would need to remember here is that you do have water. If you recognize that you don't need to know whether it's under acidic or basic conditions, you just need to remember that in addition to hydrogen ion and hydroxide ion, you also have water available for use in balancing. And you're going to need it here because that's the only way you're going to balance the hydrogens. If I start with NH3 plus O2 gives NO2 as is, then I'm going to have a problem balancing the hydrogen because there's nothing on the right that has hydrogen in it. So that's your cue to add water here. But as soon as you recognize this, you'll be laughing all the way to the bank, because at this point we have everything we need to balance this without going through all of these obnoxious steps. So let's see. The nitrogens come from the ammonia and the nitrogen dioxide, and they each contain one nitrogen. So whatever coefficient I have in front of here, I'm going to have the same coefficient in front of here. So these two are going to be locked into having the same coefficient no matter what. I do, however, need to balance the hydrogens. So let's take a look. I'm going to need at the very least a 3 here and a 2 here, because that's the least common multiple of the hydrogens that would work. But the problem with having a 3 in front of the water here is that it would give you an odd number of oxygens on the right-hand side, while on the left-hand side you only have even numbers of oxygen. We've encountered this problem before. I think we encountered that problem in part 1 of the series towards the end when we were balancing combustion reactions. Odd versus even logic. How did we fix that? We doubled both sides. So instead of having a 3 and a 2 here, I'm going to have a 6 and a 4 here. So I'm going to put a 6 here and a 4 here. And of course, if I have a 4 here, I need a 4 here to keep the nitrogens balanced. Nitrogens are balanced, hydrogens are balanced. The wild card, the oxygen, gets balanced last, just like in a combustion reaction. We've got 4 times 2 is 8, plus 6 times 1. 8 plus 6 is 14 oxygens, so I need a 7 here. And voila, it's the same exact equation. 4NH3, 7O2, 4NO2, 6H2O. All done. Okay, let's take a look at... What do I want to do? Do I want to do one of those, or should I look at... Oh, well, that's the only set I have, so maybe we should look at one more. Let's take a look at E. We've got hydrogen peroxide, H2O2, and the permanganate ion. And that gives us the manganese 2 ion plus oxygen gas, and they have this going on under acidic conditions. The permanganate ion is pretty useful, and we'll talk about why it's so useful later, but it has a distinct color to it. It's a dark purple color, and when it gets reduced to the raw manganese ion, well, I guess I shouldn't call it raw since it's an ion, but when it gets reduced to just plain old manganese ion instead of the polyatomic permanganate ion, it loses that color. So you can actually use this as a helpful way of tracking what's going on in a reaction involving the permanganate ion. If the color of the permanganate ion is fading, then you know it's being turned into the manganese 2 ion, which, you know, might be useful in some cases when you're trying to figure out whether or not you've completed a certain reaction, a reaction whose completion depends on the elimination of all the permanganate ions in the solution. We'll talk about that soon enough, though. So let's go ahead and switch to our camera again. And let's take a look at I guess that would be the reduction of the manganese ion. The permanganate ion is a pretty common oxidizing agent. It's a really strong oxidizing agent. We've got, let's see, H2O2 plus MnO4 minus yields Mn2 plus oxygen gas. All right. So if you look at the oxidation numbers, there is something a little strange going on here too. The manganese is going to be reduced, so permanganate oxygen is going to have a -2 oxidation state, and the manganese is going to have a +7. +7 and 4 times -2 gives you a total of -1. So the manganese is going to be reduced from +7 to +2, but oxygen has two different things happening to it. Well, actually no, just one different thing happening to it, but two different oxidations. So in the peroxide ion, remember, oxygen has an oxidation state of -1. Hydrogen is a +1, but hydrogen isn't going to change. And then over here, the oxygen has an oxidation state of 0. So this is interesting because you've got oxygen going from -1 to 0, but also from -2 to 0. And sometimes you might even have some -2 oxygen here, in which case you might have some oxygen going from -1 to -2 being reduced, and other oxygen going from -1 to 0 being oxidized. So sometimes you will encounter elements in a reaction that both get oxidized and reduced. That can happen sometimes, so don't be too weirded out if you run into it occasionally. Back to the main problem. So my non-oxygens and non-hydrogens, I've got the permanganate ion has manganese in it, so I'm going to want that paired up with the manganese 2 ion for a half reaction, and then everything else can go into another half reaction. So the hydrogen peroxide and the oxygen gas can go into another reaction, or a half reaction, I should say. Okay, so let's see, balance the non-oxygens and non-hydrogens. All I have is manganese, one here versus one here. It's balanced. Now balance oxygens with water. 4 oxygens here. I'm going to need 4 waters to balance those oxygens. Over here, 2 oxygens were good. Now balance hydrogens. We've got 4 times 2 over here, so I'm going to need 8 hydrogen ions. Over here we've got 2 and none, so I'm going to need 2 hydrogen ions here. By the way, for those who might be wondering, if you were doing this under basic conditions, you could at this point preemptively add the hydroxides if you wanted to, but for me it just kind of makes more sense to leave it at the end, because that way you kind of have a system where you follow the same set of steps every single time, and if it's under basic conditions you just add 2 extra steps to modify the process. I think it's easier in my mind to remember the steps if you do base conditions the same as acidic conditions up until you need to add the hydroxide. It'll make it easier to remember. But yes, you can absolutely balance the or you can neutralize the hydrogens with hydroxides at this point. Just remember to add equal amounts of hydroxide on both sides of both half reactions, which is going to end you up with some hydroxide left over on both sides of the reaction when you add the 2 half reactions, which you're then going to have to partially cancel out anyway. So I guess that's another disincentive to doing it too early, is that you might be wasting some time doing work that you're going to at least partially undo. Back to the main problem though, we've got the hydrogens are balanced. Now we go for charge. So we've got 8 positives plus 1 negative is a positive 7. We've got 2 positives here, so I'm going to need 5 electrons. 5 electrons plus 8 hydrogens, so that's positive 3. And minus 1 more, that's positive 2. And here, positive 2 plus 0. Okay, positive 2 and positive 2, that works. Here I've got 2 hydrogen ions with a positive 1, and that's the only source of charge here, so just add 2 electrons here, and we are good to go. 0 on both sides of that one. It doesn't matter that for the first half reaction, it's positive 2 on both sides, and for the second half reaction, it's 0 on both sides. That doesn't matter. I know I mentioned it earlier, but I want to emphasize again, it doesn't matter what the charges are on either side of the equation. All that matters is that they are equal to each other. Okay. So now we just balance the electrons of the 2 half reactions before addition by using the least common multiple. Between 2 and 5, that would be 10, so I'm going to multiply everything here by 2 and multiply everything here by 5 and combine. The electrons will cancel out, so I'm not going to bother writing them. 2 times 8 is 16 hydrogen. 2 times permanganate is, well, 2 permanganate. And then here, 5 times hydrogen peroxide is 5 hydrogen peroxide. Yields 2 times manganese 2. 2 times 4 water is 8 water. It looks like I have some hydrogen to cancel on both sides. That's unusual, but it's doable. Where was I? So 2 times that and 2 times 4 is 8 H2O. 5 times oxygen, so that's plus 5 O2. And then 5 times 2 hydrogen is 10 H plus. And there we go. Let's cancel out our repeat hydrogen ions. So subtract 10 hydrogens here and subtract 10 hydrogens here. And that leaves us with 6 hydrogens over there. So 6 H plus 2 permanganate plus 5 water, or no, 5 hydrogen peroxide, I should say. I think it's also called heavy water, or no, I think heavy water is when you use one of the isotopes of hydrogen. 2 manganese 2 ions, 8 water, 8 water. For a minute there I thought I had water on both sides, plus 5 oxygen gas. Okay, and there it is, balanced under acidic conditions. If we want to balance it under basic conditions, neutralize the hydrogen ions with hydroxides. So add 6 hydroxides. If I add 6 hydroxides to that side, I better add 6 hydroxides to this side as well in order to keep everything balanced. This is going to create 6 waters here, and the 6 waters there, I can subtract 6 waters from both sides, leaving just 2 waters there. Normally I would just do that mentally, but for this video I'm just going to write it all out so as not to confuse anybody. 6 water plus 2 permanganate plus 5 hydrogen peroxide gives us 2 manganese 2 ion plus 8 water plus 5 oxygen gas plus 6 hydroxide. Subtract 6 water on both sides. And if I do that, I'm finally left with 2 permanganate ion. Can you see that part of the paper? Yes, you can. Plus 5 hydrogen peroxide yields 2 manganese ion plus 8 minus 6 leaves 2 water plus 5 oxygen gas plus 6 hydroxide. And there we go. That's balancing under acidic and basic conditions. Acid balanced is what we have in green right here, and base balanced is what we have in blue at the bottom. And I think those are all the examples you will ever need to see to master the art of balancing redox equations using the half reaction method under acidic or basic conditions or even neutral conditions. Let's take a look at the last few topics for this video before we wrap things up. So now that we've learned about, in the previous video, precipitation reactions, and in this video about acid-base reactions and redox reactions, let's take advantage of all three of those so that we can develop some quantitative analysis methods. Let's introduce the concept of titration. Let's introduce the concept of titration. Titration. What is titration all about? So with a titration, you're always going to have two major reactants. One is called the titrant. The other, you could just call it the sample, or you can also call it the analyte if you want to be technical about it. So the titrant is the substance that's used in the titration. It's a known substance, and by known, I don't just mean we know what it is, I also mean we know things like its concentration or how much of it we actually have. It's a known substance, it's a measured substance. We know its concentration or some other property. We know its concentration or some other property that tells us how much of it we are dispensing. And of course the titrant and the analyte are, well, I guess just the titrant has to be something that's soluble in water. The analyte doesn't necessarily have to be soluble. I guess a titration could still work as long as the titrant can react with it, but analytes are usually also in aqueous solution as well. They're usually dissolved as well. The analyte is the unknown substance, as in it's a substance of unknown amount. We don't know how much of it we have. We don't know how much of it we have. And the whole idea is that if you know that your analyte can react with your titrant, then based on the amount of titrant you have to use in order to react all of the analyte, you can calculate how much analyte must have been in there. We did this last time when we took a look at an example of gravimetric analysis. We knew how much, what was our gravimetric analysis problem? I've already forgotten it. I think it was something having to do with magnesium sulfate, was it? Or barium sulfate? But we were able to measure the amount of sulfate ion we were able to precipitate out as barium sulfate, and based on that we were able to calculate whatever amount of barium sulfate we had gave us the amount of sulfate, which gave us the amount of whatever the original thing was. I think it might have been magnesium sulfate or something like that. So we can do the exact same thing here. If we know how much of a titrant we dispense in order to completely react with our analyte and get rid of all of it, completely react with all of it, then we can take that and kind of reverse engineer the process to calculate how much analyte must have been present before we started the whole titration process. But the key here is we need something to tell us when the amount of titrant we added is just enough, because when we do a titration, we run the risk of accidentally adding too much titrant. This is not a problem with gravimetric analysis, because with gravimetric analysis, if you add too much of your ions, then that's okay. There's only a limited amount of precipitate you can make. The analyte is a limiting reactant, and the precipitate that you get out of it is going to be limited. The analyte is still, I guess, a limiting reactant here, especially if you add way too much titrant. But the problem here is with the analyte, when it reacts with the titrant, it may not necessarily produce a precipitate that you can then separate off from the excess ions and measure individually. So there's an additional problem here. We need some sort of visual indication that the titration has stopped so that we don't add too much titrant and overestimate the amount of analyte added. So with acid-base titrations, which are going to be the most common types of titrations we will see, the indicator is actually called an indicator. With acid-base titrations, the indicator is usually some sort of acid-base indicator, special dyes that change color when the acidity level changes. So once the compound becomes, or once the mixture becomes neutral, the color will change. So acid-base titrations use acid-base indicators to determine when enough titrant has been added. So they use acid-base indicators, and one of the most common acid-base indicators is called phenolphthalein. Let me see. Am I spelling it right? It's PHTHAL, and I think it's EIN. Don't quote me too much on the spelling, but I think that's how you spell phenolphthalein. Let me take a look at the illustration in my book so that you can actually see that process. Where is my... there it is. So again, I'm gonna want to rotate the camera to show this. Okay, so those three images illustrate different points in time for an acid-base titration. So for an acid-base titration, in your what's it called? In your burette, that's this thing, this device that dispenses your titrant. Your titrant can either be an acid or a base. Whatever you put as your titrant, the opposite is going to be the analyte. So it looks like in this case the titrant is a base and the analyte is some sort of acid. So what's going to happen at first is that this solution is going to be very acidic, and there is some phenolphthalein that you add in there. It's not going to affect the reaction in any way, but it will give us some indication when we're actually done titrating. So phenolphthalein under acidic conditions, when the acidity is really high, is clear, it's colorless. But when the acidity drops, then it will turn pink, and if you keep adding base after that, it'll just stay pink. So the idea here is that you're gradually adding base through this burette, drop by drop by drop, and once you get closer and closer to what's called the equivalence point, the point where the amount of base added is getting close to being enough to completely neutralize the acid, you're going to start seeing these pink swirls kind of linger and take time to vanish. That's because they're taking time to react with the few acid particles, in this case hydrogen ions, that are still left inside this flask. But once you've used up all those excess hydrogen ions and you've neutralized all of them, the next drop you add doesn't fade. And that next drop you add is going to actually get it slightly past neutral, and it's going to make your solution slightly basic, but that's okay because at the end of the day, it's just one drop. It's not going to mess with your calculations too badly. So this is what's called the end point. Not to be confused with the equivalence point. The equivalence point is when you exactly neutralize all of your acid with an appropriate amount of base, no leftovers. The equivalence point is one drop past the end point and can still be treated as if it is the equivalence point because, again, one drop, not going to mess with your calculations too badly. If we were to reverse this process, if your analyte was a base instead, then fine. It'll start off pink and then you'll gradually add acid as a titrant to it until eventually it comes clear, and that's when you know you've reached the end point going in the opposite direction. So you can use it either way, but usually, in my experience, the lab experiments that teachers tend to do start with you having something clear and waiting for it to turn pink. But yeah, once you see that color change, you know that you've added enough titrant. So that's for acid-base titrations. There are other types of titrations which require other types of indicators, but definitely acid-base titrations seem to be the easiest titrations to get good indicators for. So have fun doing that in the lab whenever your teacher gets to it. I remember when I was taking AP Chemistry, we did, I don't even remember how many times we did titrations, but we did several titrations. We definitely did several of them. So those are acid-base titrations. Other types of titrations, we've got precipitation titrations. Precipitation titrations, basically the same process. You have some sort of analyte and you're adding some sort of known solution as a titrant, and eventually once you reach your equivalence point, once you've completely reacted your analyte, there's going to be some sort of color change, but not all precipitation reactions give us color changes that really indicate that the reaction has stopped. For example, you could keep dripping, I don't know, silver nitrite into a hydrochloric acid solution, and you'd precipitate out some white solid silver chloride, and I guess you could, if you really wanted to stare at it really carefully, you could watch drop by drop, see if more precipitate continues to form, and the moment you add a drop that doesn't seem to create any new precipitate, you could say you've reached your end point, but that's not really a good visual. We need something really good like the phenolphthalein, a color change that you can see across the whole analyte that you couldn't miss. Something that doesn't require you to have amazing eyesight. That would be nice. So with precipitation titration, we're kind of limited. There are some precipitates that add a unique color to a solution. I think silver chromate is one of them. Let me double check. I think I have it here. No, I don't have it. Well, I'm pretty sure it was silver chromate. Something about switching from a yellow color to a reddish brown color. But yeah, I'm pretty sure it was silver chromate, but I'll just have to double check it and correct myself if I'm wrong in a pinned comment. Silver chromate, I'm pretty sure, is what they use as a sort of indicator. And of course, if you're trying to do a precipitation reaction with something that isn't going to precipitate with silver chromate as your indicator, or is going to mess with the indicator's color in some way, then you're not going to be able to make good use of this indicator. So you won't be able to use this every single time. Precipitation titration is kind of limited in its utility. Similarly, there's something called redox titration. And for redox titrations, the indicator that we like to use is the permanganate ion. For redox titrations, we use the permanganate ion, either in the form of sodium permanganate or potassium permanganate, usually. Use permanganate ion as your indicator. Of course, this is also limited in its utility because we can only use it for those reactions where something actually will reduce the permanganate ion. So you can't use this, we can use it on this example here with hydrogen peroxide as our titrant, but we wouldn't be able to use it with some other titrant that doesn't, or with some other analyte, I should say, that interferes with the permanganate ion's ability to get reduced. So precipitation titration and redox titration, we have much more limited use for our indicators because the indicators we have only work under specific circumstances. You can't redox titrate every redox reaction imaginable, and you can't precipitation titrate every single precipitation reaction imaginable, but we do have plenty of useful acid-base indicators. So almost all of the titrations we're going to encounter, the vast majority of them are going to be acid-base titrations. So commenting on redox titration further, the permanganate ion, what's really great about it is something I mentioned earlier. It has that pink color to it that or sorry, not pink. It has this dark purple color to it. And in fact, let me show you this visual about the permanganate ion. So permanganate, it's dark purple, and our government claims that it's safe to drink. This is actually recent news. If you want to look up that YouTube video, there's the title in front of you right now. Yeah, permanganate ion, it's used as a common oxidizing agent, and apparently something happened in, I think this was in 2 states. One of them was Ohio, I forget the other one, it might have been Pennsylvania, where some people started getting purple water coming out of their taps, and that's because of some excess permanganate ions, excess permanganate ion that didn't get filtered out somehow. I mean, in water treatment facilities, they do use permanganate to get rid of unwanted substances, but they usually get rid of the permanganate ion before it reaches your house. Anyway, that's what permanganate ion looks like. And when you reduce it to the regular manganese 2 ion, or even to manganese 4 dioxide, you lose the color, and that gives you some indication that the redox reaction you were performing has reached completion, if, you know, it interacts properly with the permanganate ion. Again, redox titrations, limited utility. Okay, so let's go ahead and take a look at some examples of each of those titrations, or at least the calculation that results from those titrations, and then we can call it a day here, or a night, depending on when you're watching this. Let's go ahead and look over here. So, these are just stoichiometry questions at the end of the day. Hold on, I think I'm forgetting something. There was something I wanted to mention. It was on my mind earlier. I know I'm forgetting something, and I'm gonna feel silly once I remember it. What is it? What is it? Oh, goodness. I think it was something to do with acids and bases. Oh well, it'll come back to me whenever it comes back to me. Let's see. So we've got number 78 says, what volume of 0.0105 molar hydrobromic acid solution is required to titrate 125 milliliters of 0.01 molar calcium hydroxide solution? The equation is given right there, and I just remembered what it was I wanted to say about acids and bases. One last comment about those before we do that problem. So, I probably should have mentioned this much sooner, but phenolphthalein and another indicator, bromthiamyl blue, I believe, are indicators that are really good to use when you're titrating strong acids and strong bases, when your titrant and analyte are strong acids or bases. For weak acids and bases, phenolphthalein and bromthiamyl blue may not work so well. Your equivalence point might be past the point where you have equal amounts of titrant and analyte, or I shouldn't say equal amounts, but equivalent amounts. So we need to make sure we can recognize what a strong acid or base is. And the only way to recognize them really is to memorize them. So, strong acids. These you have to memorize. Strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, perchloric acid, and according to some people, chloric acid. Your teacher may disagree on this last one, but chloric acid is recognized by some chemistry textbooks and several chemistry professors as being a strong acid. Strong bases, these I just kind of like to memorize their positions on the periodic table more than anything. Strong bases are basically all of the soluble hydroxides. So if you remember the solubility rules for hydroxides, then all of the soluble hydroxides are your strong bases. So if we look at the periodic table, they're going to be the hydroxides of all the group 1 metals and some of the group 2 metals. So they're going to be sodium hydroxide, lithium hydroxide. I probably should have written that one first. Lithium, sodium, potassium, rubidium, and cesium hydroxides. All of those are strong bases. Calcium hydroxide is a strong base. Barium hydroxide is a strong base. And strontium hydroxide is a strong base. So again, the way I remember these is I just kind of visually remember their location on the periodic table. Lithium, sodium, potassium, rubidium, and cesium are all in that red block of the periodic table that we like to use. Maybe I should pull that up real quick. So they're all in that red block. And then for the orange block, basically skip the first two. Skip beryllium and magnesium. Calcium, strontium, barium, their hydroxides will be strong bases. As for francium and radium at the bottom there, I believe those are both radioactive, so we can't really say much about them one way or the other, but I would predict that if we ever could get stable francium hydroxide or stable radium hydroxide, that they would both be strong bases as well. Just following from the pattern, but you never know. Okay, so these you must commit to memory. One other note, strong acids and strong bases are also strong electrolytes. We talked about electrolytes in the previous video. In the previous video, we showed strong electrolytes, they dissociate completely into ions. In other words, these are perfectly soluble. They're not just partially soluble, they're perfectly soluble. There will be a chapter where we talk about weak acids and weak bases, which are basically every other acid and base in existence. And don't be deceived by the term weak. Weak means partial dissociation, but even among weak acids and bases, there are some really strong weak acids and some really weak acids and some really strong weak bases and some really weak bases. Once we get to the acid-base equilibrium chapter, we'll investigate those a little bit further. But yeah, commit these to memory. Okay, let's go ahead and go back to that problem that I was in the middle of starting before I remembered all that. So, gonna read it again. It was problem 78. What volume of that hydrobromic acid solution is required to titrate 125 milliliters of a 0.01 molar calcium hydroxide solution? It's ultimately a stoichiometry problem. So let's go ahead and copy down the information. The chemical equation will definitely be helpful. So I've got calcium hydroxide strong base plus 2 hydrobromic acid yields calcium bromide plus water, 2 water in this case. And we are given the molarities of both solutions. So for the hydrobromic acid, we've got 0.0105 molar. And for the calcium hydroxide, we've got 0.0100 molar. And we've got 125 milliliters of it. So normally in a titration, you would not know what the molarity of this calcium hydroxide is, but you would know the volume, and then you would measure the volume of hydrobromic acid that you add to it in order to neutralize it and get that color change. And once you've got that color change, you can work backwards and do the math to calculate that the concentration of that calcium hydroxide must have been 0.0100 molar to begin with. But here they've given us the conclusion ahead of time, and that's fine. So they're asking how much hydrobromic acid do I need to dispense from my burette, which holds all of my titrant, in order to reach the end point. Okay, so 2 different ways to do this. One way is the easy way if you're on top of your mental math skills. If you've got good mental math skills, then you might be able to get through this the quick and easy way. But if mental math isn't your thing, that's fine. You can still fall back on regular old stoichiometry. So we've got 125 milliliters of calcium hydroxide. And of course we're going to need to convert that to liters. Every 1,000 milliliters is 1 liter. Multiply your liters of calcium hydroxide by molarity of calcium hydroxide. Every 1 liter of calcium hydroxide contains 0.01, I don't know what happened with that, 0.0100 moles of calcium hydroxide. And then for our moles of calcium hydroxide, we can cancel with 2 moles, or sorry, no, other way around. 1 mole, I guess I'll just write it here. Every 1 mole of calcium hydroxide, according to our equation, reacts with 2 moles of hydrobromic acid. And of course, our hydrobromic acid, every 0.0105 moles of it is 1 liter. And usually this number is going to be a small number of liters, which we may be better off converting to milliliters. So I may want to multiply this by 1,000 milliliters per liter, but we'll see what we get. So if I go ahead and crunch the numbers, 125 over 1,000 is just 0.125. Times 0.0100 is 0.00125. We still have 3 sig figs. 0.00125. What is going on with my zeros? So that's moles of calcium hydroxide. Multiply that by 2, you get moles of hydrobromic acid needed, so that's 0.00250 moles. And then divide that by 0.0105. So times 2 and then divide by 0.0105. and I'm getting 0.238 liters if I round to 3 sig figs, which is also equal to 238 milliliters, which is also equal to 238 milliliters. So you'd probably have to refill the burette multiple times, because I think most burettes I've ever worked with don't hold more than 50 or 100 milliliters of titrant at a time. Okay. Now, how do we do this the easy way? So the easy way is to use what's called normality. The easy way to do this is to use something called normality. Normality. Normality is based on molarity. The normality of an acid or a base is simply its molarity times the number of equivalents of acid or base in it. So normality equals molarity times the number of equivalents. EQUIVALENT, equivalents with a T, not equivalence with a CE. Equivalence with a CE is what I was mentioning earlier when I was talking about equivalence points. Here I'm talking about equivalents. So what is this number of equivalents that I've mentioned here? What is it all about? Basically, it's about the net ionic equation in any acid-base reaction. Remember, for any acid-base reaction, ultimately, an acid-base, I shouldn't say in any acid-base reaction, but in any acid-base neutralization, the net ionic equation is H plus OH minus gives us H2O. So it doesn't matter that it's calcium hydroxide. I could have substituted this with any of my strong bases. All that really matters is the hydroxide ion here. Same thing with the hydrobromic acid. I could have used hydrochloric acid. I could have used sulfuric acid. I could have used any other strong acid, and I would have been fine, because all I need out of the acid is the hydrogen. So since the hydrogen and the hydroxide are really what need to balance each other out, are what need to exist in equal amounts in the solution in order to completely neutralize, just count the number of hydroxides or hydrogens in these substances. So the calcium hydroxide has 2 equivalents of hydroxide ion in it, while the hydrobromic acid, it only has 1 equivalent of hydrogen in it. Sulfuric acid would have 2 equivalents of hydrogen, and among the strong bases that's the only one, though that second hydrogen removed from sulfuric acid has some complications to it, which we'll talk about when we discuss acid-base equilibria in a much later chapter. So the molarity of the calcium hydroxide may be 0.0100 molar, but that's moles of calcium hydroxide per liter. How many moles of just hydroxide are there per liter? If I've got 0.01 moles of calcium hydroxide, then I have 0.02 moles of hydroxide. So the normality of the calcium hydroxide, or the concentration of the hydroxide in it, in other words, is 2 times the concentration of the calcium hydroxide as a whole. So if I use normality, then I can use an equation very, very similar to the dilution equation that we mentioned in the previous part. The dilution equation was M1V1 equals M2V2. Well, in this case, if you want to do an acid-base titration, you can use normality. N1 times V1 equals N2 times V2. The justification for the dilution equation was that molarity times volume equals moles of solute, which is supposed to be the same at the beginning and at the end after you water your solution down. We can make the same argument here. N1 V1 times N2 V2. Normality times volume is concentration of hydroxide, or hydrogen times volume, which just equals the moles of hydroxide or the moles of hydrogen. And since the moles of hydroxide have to be equal to the moles of hydrogen, N1 V1 equals N2 V2 makes perfect sense. In fact, some people will actually write this as Na Va equals NB VB, where the A and B stand for acid and base. And that's perfectly fine. But yeah, if we use this formula, we can quickly get 238 milliliters, because here's how this would play out. The normality of calcium hydroxide is its molarity times 2, since it's got two hydroxides in it, so 0.0200, and that would be its normality. For the hydrobromic acid, it's only got one equivalent of hydrogen, so 0.0105 times 1 is going to be still 0.0105. Okay, so we've got the normalities, and I know the volume of the base, so I guess I'll write it over here. We can do normality of acid 0.0105 times volume of acid equals normality of base 0.0200 times volume of base, which is 125 in milliliters. If I plug in milliliters here, and both of these are in the same units of moles per liter, the units of the normalities will cancel out, and that just leaves me with milliliters, so I don't have to necessarily convert to liters when using this method, though you can if you want to. So 0.0105, I'm going to divide both sides by that, and if I do that, I get 0.0200. Whoops, somehow missed the decimal. 0.0200 divided by 0.0105 is 1.90. 1.90 times 125 is 237.5, which rounds to 238. Va is equal to 238 milliliters yet again. So that's the easy way to do this type of problem, is to take advantage of normality. Make sure you understand it before you use it. I'm not against the use of shortcuts, but I am against the use of shortcuts that you don't understand. When you use a shortcut you don't understand, one day you'll use it when it's not really a shortcut. And on that day, you'll probably blame me for teaching you everything wrong. And I'll just kind of shrug and hope that the next student heeds my warnings. Let's go ahead and look at another acid-base titration. So the other problem, it is acid-base, right? Yeah. Titration of a 20 milliliter sample of acid rain required 1.7 milliliters of 0.0811 molar sodium hydroxide to reach the end point. If we assume that the acidity of the rain is due to the presence of sulfuric acid, what was the concentration of sulfuric acid in this sample of rain? Okay, so that is actually a proper titration problem. So we've got 20 milliliters of sulfuric acid. First, let's write the neutralization equation. H2SO4 plus NaOH gives us, of course, sodium sulfate is our salt, and water. And yeah, we are going to get 2H2O. We're going to need a 2 there, and that's perfect. So let's see, given values, we have 20 milliliters of acid rain, so that's 20.0 milliliters containing sulfuric acid. And we needed 1.7 milliliters of sodium hydroxide to titrate it. The sodium hydroxide was 0.0811 in its molarity. If we assume that the acidity of the rain is due to sulfuric acid, what was the concentration? Okay, so we got all the data. So again, we could just take advantage of normality here and work this out. You might be better off using stoichiometry if you don't fully understand how the normality shortcut works, because here's something we haven't discussed yet about normality. What happens when you have something with an unknown concentration? How do you get its normality? Or how do you represent its normality? Some of you are already on top of your math game and you know exactly what to do here, which is great, but others may want to proceed with more caution. So let's see. Again, I just want the numbers of hydrogens to equal the numbers of hydroxides by the time I reach the end point, and they said that at these volumes the end point is reached. So let me think here. I guess I'll do stoichiometry first, and then we'll take a look at how to do it using normality. So I'm going to start with my 1.7 milliliters of sodium hydroxide, and I'm going to make and I'm going to convert that to liters, of course. So every 1,000 milliliters is 1 liter, and then every 1 liter of sodium hydroxide is 0.0811 moles of sodium hydroxide, and then every 2 moles of sodium hydroxide gives us 1 mole of sulfuric acid, and then every actually no, I just need my moles of sulfuric acid, and then I can divide that by, after I convert my 20 milliliters to liters, I can divide by those liters and I'll get the concentration. Okay, so that's where that ends. So let's see. 1.7, of course, converted to liters, you just move the decimal 3 places. 0.0017 times 0.0811 rounded to 2 sig figs is 0.00014. So 0.00014 moles, and then multiply that by 1 over 2 and you get 0.000070 in keeping 2 sig figs. That would be the moles of sulfuric acid in your 20 milliliter sample. 20 milliliters is 0.020 liters, so molarity of the acid in this case is equal to moles 0.000070 moles of sulfuric acid over 0.020 liters of sulfuric acid, and probably other stuff mixed in there as well. If I go ahead and divide that, that gives me 0.0035. 0.0035 molar. Okay, how do we figure this out? Making use of normality. Not too hard to do. So NV equals NV, of course, but we can also substitute normality with the expression for normality, which is molarity times the number of equivalents. So normality of acid is molarity of acid times number of equivalents of acid times VA. So this replaces Na equals MB times number of equivalents of base times volume of base. And that's all you really need to do there. So plugging in the numbers, we have for the acid, the molarity is unknown, but if it's sulfuric acid, it's got 2 equivalents. This is an exact number, by the way, times a volume of 20 milliliters. I can actually keep it in milliliters this time. I'll have milliliters on both sides to cancel out. Equals molarity times number of equivalents for sodium hydroxide. There's only one hydroxide in each sodium hydroxide, so the number of equivalents is 1, so 0.0811 times 1 is still 0.0811 times the volume of 1.7 milliliters. The milliliters cancel on both sides. And yeah, just work out the math and we should be getting the same number. So 0.0811 times 1.7 is 0.14. 0.14, if I divide by 2, is 0.07, or 0.070, I should say, to keep 2 sig figs. And then divided by the 20.0, it's 0.0035, same result as before. So we still get molarity of our acid is 0.0035 moles per liter, or 0.0035 molar. All right. Let's take a look at... I have some other acid-base titration problems here. Should we do them? Let me give them a quick read, and I'll decide whether I should just leave them to you to practice or actually work them myself. How many milliliters of 0.1500 molar solution of potassium hydroxide will be required to titrate 40 milliliters of a solution of phosphoric acid? Interesting, but not anything we haven't done before. Potassium hydrogen phthalate, KHP. Oh yes, my AP chemistry teacher really loved using KHP. It's all coming back to me. It's used in many laboratories, including general chemistry labs, to standardize solutions of base. Yeah, we can skip those. You can practice them on your own if you want to, but I'd really like to go to an example of a redox titration and a precipitation titration, and then wrap things up with that. I think there was something else that just occurred to me. It was on the tip of my tongue and I've already forgotten it. There was something I wanted to say. What was it? Oh, right. So, another name for... Let me switch back to the camera real quick. So another name for the titrant, another name for it is the standard solution. Another name for it is the standard solution. Sometimes the titrant is also called a standard because you've basically standardized its concentration. You've made its concentration something to measure other concentrations against, and so you can use titrations to standardize other solutions, to measure the concentrations of other solutions based on the standard set by your titrant, which presumably is measured to a high degree of precision. But yeah, that's just something I was reminded of when reading one of those problems. Anyway, back to this example of a precipitation titration. So we've got a 20 milliliter sample of aqueous oxalic acid was titrated with 0.09113 molar solution of potassium permanganate. Oh, that's a redox, right? Yeah, that's the redox titration. Okay, the precipitation titration will be the last example then. So a volume of 23.24 milliliters was required to reach the end point. What is the oxalic acid molarity? Let's go ahead and work it out. So back to that scene. Copying down the values, we've got, well, I'll just copy the equation first. So we have 2 permanganate ion. Notice that they don't even include the potassium anywhere in this equation because potassium is a spectator ion. In fact, most of the equations we looked at today, you had a bunch of ions just there in the equation, and presumably their counter ions, the ions that are present to counter their charge and keep the solution neutral, would have been spectator ions that we just removed from those equations. Maybe if I stopped rambling every time I saw something interesting in a question, these videos would be shorter, but I think those random rambles are valuable. 2 permanganate ion plus 5 oxalic acid plus 6 hydrogen yields 10 carbon dioxide, 2 manganese, 2, 10 carbon dioxide, 2 manganese, 2, and 8 waters. 8 waters. All right. Let's have us a look at what we've got to work with. So 20 milliliters of oxalic acid, 20 milliliters, 4 sig figs. And the potassium permanganate, we've got 0.09113 molar. So 0.09113 molar is the molarity of the potassium permanganate, and 23.24 milliliters of the titrant, which in this case is the potassium permanganate, and we know that because they said was titrated with, let me put it back up on the screen, it says right there in the first line in the middle, was titrated with a solution of potassium permanganate. You titrate with your titrant. Whatever you titrate something with, that's your titrant. So 23.24 milliliters of titrant. And I guess the other way you know that this refers to the permanganate is because we already know the volume of the oxalic acid. Okay, so what is the oxalic acid molarity? In this case, how would I go about using normality? I guess I would just use the mole ratios to come up with normality, but I feel safer just using stoichiometry for this problem. Redox titration questions are rarely asked of you, so you might as well just be careful with it. You know, using the normality shortcut for acid-base titrations is fine because we do a lot of acid-base titrations. We'll get to use that shortcut a lot and be familiar with it and not screw it up. But here, I'm not too familiar with the shortcut, so I don't trust myself too much. I'd have to practice it a couple times to get a feel for it and really feel like I know what I'm doing. So it's really just more stoichiometry. You've got 23.24 milliliters, and I'm going to introduce the concept of the millimole now because it's pretty common that you're going to get volumes given in milliliters, and it gets kind of annoying after a while converting milliliters to liters every single time. So here I'm going to introduce the concept of millimoles. If instead of converting my milliliters to liters, I just leave them as milliliters, I can go ahead and write for every 1 milliliter, I get 0.9113 millimoles. Right? If 1 liter gives you 0.09 moles, then 1 milliliter, 1/1000th of a liter, should give you 1/1000th the number of moles. The millimole concept can be pretty useful when you don't want to have too many zeros beyond your decimal point, like what we had in the last problem. Was it the last problem? Yeah. So yeah, I'm going to work in millimoles here. So converting these milliliters to millimoles, that's one step, and then this is millimoles of permanganate, so every 2 millimoles of permanganate requires or gives you 5 millimoles of oxalic acid, and that would give us the millimoles of oxalic acid, which divided by the milliliters of oxalic acid will give us the moles per liter because the millis will cancel out. So let's go ahead and get our millimoles of oxalic acid. 23.24 times 0.09113. If I round to 4 sig figs, that's 2.118 millimoles. Millimoles. Times 5/2, that's an exact conversion. We keep 4 sig figs, 5.29, and that rounds up to 5. 5.295 millimoles of oxalic acid are what we have. So if I go ahead and calculate the molarity of oxalic acid, it's going to be 5.295 millimoles over 20.00 milliliters, which is the same as moles over liters because milli is just 10 to the negative 3, so 10 to the negative 3 cancels with 10 to the negative 3, and you get the molarity in moles per liter, or you get the concentration in molarity, which is moles per liter. So 5.295 over 20.00 is going to be 0.2648. 0.2648 moles per liter, or 0.2648 molar. All right, and our last example is going to be this precipitation titration. Oh, actually we have a couple of precipitation titrations. Which one do I want to do? I think I want to do the second one. Let's do 81. In a common medical lab determination of the concentration of free chloride ion in blood serum, a serum sample is titrated with a mercury 2 nitrate solution. And the net ionic equation is 2 chloride plus mercury 2 nitrate yields 2 nitrate ions plus mercury 2 chloride. In fact, that's not the net ionic equation because the nitrates are spectator ions. Once you eliminate those, you've got the net ionic equation. Anyway, what is the chloride concentration in a 0.25 milliliter sample of normal serum that requires 1.46 milliliters of 8.25 times 10 to the negative 4 molar mercury 2 nitrate to reach the end point? Let's copy the equation and all the other useful data. So first I've got my equation. So 2 chloride plus mercury 2 nitrate yields 2 nitrates plus mercury 2 chloride. So notice that we don't even care about the indicator that they used for any of these titration problems that we've done so far. You'll care about the indicator used when you actually do it in the lab. But we can only presume that they used an indicator that was good enough that their estimation of the endpoint was fairly precise, even if not perfect. So, other information given. We have 0.25 milliliters in our blood serum sample, so 0.25 milliliters. Our titrant, we used 1.46 milliliters of it. And it had a concentration of 8.25 times 10 to the negative 4 moles per liter. And they want us to figure out the chloride ion concentration. Okay, very, very similar to the previous problem, in fact. So I'm going to start with my 1.46 milliliters of my known, in this case my mercury 2 nitrate, 1.46 milliliters. And I'm going to say for every 1 milliliter, I get 8.25 times 10 to the negative 4. Can I fit it in? Millimoles. And it barely fits. I don't think you can even read that. It looks like a big scribble, but it's supposed to say millimoles. Multiply that by, let's see, so that's millimoles of mercury 2 nitrate, and then for every 1 millimole of mercury 2 nitrate, we get 2 millimoles of chloride ion. 2 millimoles of chloride ion. And once you've got your millimoles of chloride, we can divide that by the milliliters of chloride to get the moles per liter. So 1.46 times 8.25 times 10 to the negative 4 rounding to 3 sig figs is 0.0012 millimoles. 0.0012 millimoles. And then if I multiply that by 2 over 1, that's 0.0024. Oh, I should actually have another 0 here, since it's 3 sig figs. Millimoles. Okay, almost made a mistake there. Let's see, and then once we've got that, that's your millimoles of chloride ion, so take your 0.00240 millimoles of chloride over 0.25 milliliters of chloride. The millis cancel out. They're just a factor of 10 to the negative 3 at the end of the day. And we are left with, rounding to 2 sig figs, 0.00240 divided by 0.25 is 0.0096. 0.0096 moles per liter, or molar. And there we go. That is an example of a precipitation titration. Of course, we didn't really see anything precipitate here, but at the end of the day, we did cover the part that matters, which is the calculation at the end. I mean, I'm not saying that the process doesn't matter, because if you mess up the process in the lab, the numbers you get are going to be bad, and with bad numbers come bad results. But yeah, that's everything you wanted to know about reactions involving ions. A lot of our equations today had a bunch of ions in them, and yeah, there's ionic equations. So next time the plan will be to cover gas laws. We're going to cover everything there is to know about gas laws, and we're finally going to introduce the concept of molar volume, which I mentioned in the previous video. We'll finally get to see the last, I guess you could call it, pathway in our stoichiometry flowchart from last time. So look forward to that. I plan on getting that video ready sometime this weekend, if not earlier. So look forward to it whenever it comes out. And I think that's all I have to say. Hope you learned a lot today. Hope this has been helpful as always. And I guess I'll just give you your regular reminder. This has been Al the Tutor, reminding you that ignorance is not bliss. Take care, and I'll see you in the next video.